Welcome everyone to the 9th ADGA. The first talker is Krzysztof, and it's my pleasure to have you as the first speaker. And Krzysztof is a research scientist in IBM, and he's been doing a lot of research in sublinear computing, in models such as massively parallel computing, dynamic algorithms, and streaming. And to not spoil his talk for him, I let him introduce his topic for today, and now you can take the stage.
Thanks. It is my great pleasure to be speaking at this workshop on advances in distributed graph algorithms. So I'm at IBM Research, and today I'm mostly going to be talking about recent developments in massively parallel algorithms for graphs. Let me start with a little bit of background where it all is coming from. So essentially, at some point, the sizes of data sets that people have to deal with have grown to the extent where it was no longer possible to efficiently process them on a single machine or even a small number of machines. And to address this practical need, people started developing massive data processing systems, right? The most popular ones are probably MapReduce, Hadoop, Spark. So the nice thing about those systems is that they can be deployed on a cluster of pretty much regular computers. So there is no need to spend a lot of money on a very expensive supercomputer. This setting, however, poses its own challenges, right? So once you distribute a data set across a large number of machines, there is no single machine that has full access to all of the data. So now you have to come up with some way for those machines to cooperate in order to solve the problem. And for most problems, they will also have to talk to each other, right, in order to solve a specific problem. So the challenges here are, figuring out how to minimize the total amount of communication and also how interactive this computation has to be. So the most popular model for this type of setting is massively parallel computation. It has had various names over the years, but this is something that it seems the community has converged on. I'm gonna sometimes refer to it as simply as MPC. And so it was introduced by Karlov, Sully, and Wasilewski. It was inspired by MapReduce. The setting is roughly that we have some number of machines, let's say capital M. Each machine has some local space, let's say capital S. And in our case, because we're going to be mostly talking about graph algorithms, the input is going to be some set of edges, let's say little m, and the graph in which those edges are is going to be on n vertices. So the computation in this model starts from each machine receiving its share of the edges, right? And then it proceeds in rounds. So this is depicted in the picture. It goes from left to right. Basically, there are synchronous rounds. In each round, first, each machine performs some local computation on the data it has. And then at the end of the round, machines exchange messages. Any machine can send a message to any other machine. The only limitation is that the total length of messages that the machine sends and receives is bounded by its local space. You can think of this as requiring that each machine first pre-computes all the messages it's going to send in its local space, and then it also puts all the messages in its local space before it starts processing them. So this is the general setting, but there are various parameters that I mentioned, and so the question is now, what settings of those parameters make sense? So first, an essential part of the model is the assumption that this local space per machine is going to be at least the input size to some constant greater than 0. In particular, it's in most cases you can even assume that the local space is at least the square root of the total space, the input length, and this is a very important assumption that allows for lots of very useful primitives basically we can execute them in a constant number of rounds, like things like sorting, prefix sum, and many other simple tools. When it comes to the total space, which is the number of machines times the local space of each machine, in general we strive to keep it close to linear in the input size. The reason is that if you are dealing with a huge data set, then most likely you won't have that much extra space in order to perform computation on it. And when it comes to graph algorithms, it's very useful to parameterize the local space of each machine in terms of the number of vertices. So there are three most popular natural space per machine regimes that people have considered. The first one is superlinear. So in this setting, each machine has n to the 1 plus some constant local space. You can think of this as each machine being able to store a non-trivial amount of information about every vertex in the graph. Then there is the linear or near linear space regime. So in this regime, it's slightly less. Now you can still essentially keep some information about every vertex, but it's not going to be too much. And finally, there is the sublinear space regime, in which the local space per machine is n to d alpha, right? Where alpha is a number between 0 and 1, is a constant between 0 and 1. And this is the most interesting regime for sparse graphs. And as we know, like many practical graphs are relatively sparse, things like transaction networks or social networks. The average degree in those networks is relatively low. So if you want to distribute the computation for such a graph across a large number of machines, it has to be in this space regime when the space per machine is sublinear, right? And let me once again stress that whenever I'm going to talk about superlinear, nonlinear, or sublinear throughout the talk, I don't mean the total space, but just the space per machine. So the main goal for this line of research has been minimizing the number of rounds that an algorithm requires. Since many people here are going to be interested in this, let me just mention very briefly that for most algorithms in more classic models such as PRAM, local congest, it's usually possible to take those algorithms, unless they have some crazy features, and simulate them in essentially the same number of rounds in MPC, right? And this is going to work even in the setting with sublinear space per machine. Since many of those things run in at least a logarithmic number of rounds, it has become kind of a gold standard to obtain algorithms which are much faster, that run in a constant number of rounds, or even poly, log n, whenever a constant seems impossible. So the plan for the talk is to briefly touch on three topics. First, I'm going to mention some early MPC research. Then I'm going to talk about what is known for matchings for near linear and sublinear space, and then I'm also going to talk about approximately solving problems on MPC as opposed to solving them exactly. So early MPC research. So there are going to be two examples that I'm going to mention. So the first one is superlinear space. Right, so once you have n to the 1 plus some constant space per machine, this often allows for obtaining algorithms that run in constant number of rounds. Right? And in particular, popular complexities are 1 over delta or log 1 over delta. So algorithms in this regime have already appeared in some of the first MPC papers. So there have been many other papers that consider the space regime later on. One popular approach, it's not a very well defined what exactly it means, but one popular approach is filtering. And essentially the idea is that because we have so much space per machine, we can to some extent put too much information on a single machine. And since the solution is going to be much smaller, only linear in size, think of something like the minimum spanning tree, for instance, then this allows for eliminating lots of edges that potentially could end up in the solution. The other example I want to mention is for geometric graphs, so this is from a common paper, joint paper with Alex Andoni, Sasha Nikolov, and Grigory Yaroslavtsev. So the idea is that, so in this setting, the input is not going to be edges. It's just going to be a set of points in a, say, constant dimensional Euclidean space. And once you have a set of points in any metric space, it induces a full weighted graph, right? Where the weight of an edge is the distance between its endpoints. So in this setting, we can show algorithms that run in constant number of rounds. And even if the space per machine is sublinear. And in particular, we considered two problems, approximating the minimum spanning tree and also estimating the earth mover distance between two sets of points. And very briefly again, the general idea behind this is we showed how to adapt to MPC like a classic technique, which is geometric technique, which is based on imposing a randomly shifted grid onto a space. And this gives you some random partitioning of the space. And then you can build up a solution, first solving some slightly more general problem for small cells. And this builds up eventually to a solution for the entire data set. So for those two problems, it's not something that people really consider in this framework before. So it also required quite a bit of work to make those two problems actually work. But the bottom line is that in this regime, in this kind of setting for geometric graphs, we can obtain a sublinear space per machine, but unfortunately this requires an embedding into a low-dimensional space, or at least knowing that the points live in some low-dimensional space, such as something of bounded doubling dimension would be enough, for instance. Now, it's a very natural question. This point was, how about efficient algorithms for general graphs, right? Like if your space is near linear or sublinear per machine, right? And so at that point, that was something that I was very interested in, but I spent quite a bit of time thinking about this, and it's essentially impossible to do anything useful when you don't have something like a geometric embedding that naturally can be leveraged into a way of partitioning the data across the machines. So it was very exciting to see that over the last few years there was quite a few non-trivial developments. So I'm gonna mostly now talk about approximating the maximum matching problem, right? We just as a reminder, we have a graph. We want to find a set of vertex disjoint edges of maximum cardinality, right? That's the goal. And so what is known about this problem? So already one of the first MPC papers showed that a constant number of rounds suffice if space per machine is superlinear. Then you can also take any of the classic PRAM algorithms for maximal independent set or maximal matching and just simulate them in a logarithmic number of MPC rounds. Because their original complexity in PRAM is also logarithmic, right? And this was pretty much the state of the art in 2017 with this natural logarithmic barrier, right? And then what happened, I had a paper with Artur Czumaj, Kuba Łącki, Oleg Mądry, Slobodan Mitrović, and Piotr Sankowski, in which we showed that at least for linear space, it's possible to improve on this complexity. So we got it down to, it was essentially an exponential improvement to log n squared. Yeah, we kind of suspected that the right answer is log n, but unfortunately, like our analysis wasn't as good as all those follow-up papers that had that got log n round complexity for matchings and for various other problems. So how about the sublinear space per machine? So then some improvements there are possible as well. You can get square root of log n rounds. It also applies to other problems. So I won't have much time to talk about how to obtain these results in this talk, or even in the longer version of this talk that is online. But let me just say that one way, there are some other techniques that people developed later, but one way to get to this complexity is to use a general approach of round compression. So basically, you start with some specific algorithm that can be seen as an algorithm in the PRAM or local model that runs in a logarithmic number of rounds. And then you can take it and convert it into an MPC algorithm that runs in much fewer rounds. right? So basically you start, basically you take several rounds of this algorithm and you compress them into a constant number of MPC rounds roughly. Right. So what are the challenges in this type of setting? So the biggest one is keeping global consistency, right? Because now you're going to distribute the data across several machines that are going to try to run this distributed algorithm, and you know, if they're supposed to execute several rounds of this algorithm without communicating with each other, right? So the biggest challenge is keeping global consistency, and also there is like another feature that eventually enables making this work for matchings and related problems, which is that it's possible to execute this algorithm on a sparsified graph. And so I'm not going to go into more details here, but these are like requirements why that allow this to happen for some say packing and covering problem. It's a great question. How about like general packing and covering problem? For instance, like one thing which I don't know the answer to, like can you run it in sublogarithmic number of rounds, is, you know, can you do this for a covering problem, but for that problem, for instance, we do not know how to do this. So let me briefly compare the complexity of matchings to the complexity of connectivity. So in this problem, you want to, like the simplest version, let's say you want to find out whether the graph is fully connected. So in the near-linear space regime, matchings are require larger number of rounds, log n, while connectivity we can solve in a constant number of rounds. For sublinear space, on the other hand, matchings are simpler than connectivity. So you could ask, you know, how optimal these things are. So for connectivity, I think it's very well understood that most likely this is what the complexity should be. We have some really examples for which we do not, it's very simple examples for which we do not know how to beat a logarithmic number of rounds, but at the same time, unfortunately, we don't have techniques for proving lower bounds for this model without any assumptions. And for matchings, the status is much less clear. We are stuck where we are stuck. It might be due to the limitations of our sparsification or exploration techniques. A constant number of rounds for sublinear space is most likely not possible. So, you know, it would be great to show that the current bounds are optimal using perhaps some reductions, some other problems that are, you know, very easy to believe that are difficult. And you know, in general, I wouldn't be surprised if for sublinear space, if some improvements came at the same time as improvements for some sublinear time algorithms for estimating the matching size. This is something that people have worked on like more than a decade ago. The second recent topic I want to touch upon is solving problems approximately. So we are borrowing the approach from property testing. So for a specific problem, we want to accept things which have the property, and you want to reject things which are far from the property. For instance, for the problem of testing bipartiteness, so the exact solution would be, you know, is my graph bipartite? But here we're gonna just look at the slightly relaxed version. So I want to accept things which are bipartite, and I want to reject graphs that need to have at least a constant fraction of edges removed in order to become bipartite. Right. So, so it's very easy to show that. For the exact bipartiteness verification, most likely a logarithmic number of rounds is necessary, basically by a reduction from connectivity. But for approximate versions, we show that it's possible to check approximate bipartiteness using log n rounds, right? And this also applies to expansion testing, checking whether a graph is an expander. How is this achieved? So the popular tool in property testing is random walks. So we show how to generate random walks efficiently in MPC, even in sublinear space. Essentially, we show that it's possible to generate a small number of random walks from each vertex in a number of rounds, which is logarithmic in the length of those random walks. We can also achieve some additional results. And let me very briefly just say that there is some small incompatibility between MPC and the tool that we designed. So our tool allows for generating a small number of random walks from everywhere, but the traditional property testing algorithms usually generate a large number of random walks from a small number of vertices, right? So the question is now, can this be slightly modified and distributed? And so it's possible for bipartiteness and expansion testing. There are some other interesting questions like clusterability, minor freeness testing, where we unfortunately don't know how to do this. So those things can still be executed in log-log-n rounds, but unfortunately this happens at a large total space penalty. So the total space increases by this factor of square root of n, which doesn't seem to be something you want to do for when you're handling big graphs. So that's an interesting question. So to wrap up the talk, a bigger picture, right? So there's lots of interesting other developments in MPC that I didn't have time to talk about, including some conditional lower bounds, other types of problems like coloring and dynamic graph update, like dynamic graph algorithms. Two more specific, exciting challenges that I really like, and I have completely no idea what the answer is understanding the complexity of matchings, which I mentioned, and then designing space-efficient algorithms for some problems that can be solved using random walks. And also for the bigger picture, MPC is very synchronous, and it seems that there is more and more systems that are asynchronous, at least when it comes to systems research, right? And so the good question is, how to model this type of setting, and also is there even a theoretical advantage to it, right? Because maybe we are just smart enough, to design better synchronous algorithms that are actually not worse than whatever one would do in the asynchronous setting. And it is, I'm looking forward to the other talks. The program of the workshop looks very exciting, and I'll be happy to take any questions. Yeah, so do you have a guess on what is the right round complexity for matchings in the sublinear memory regime? For instance, more like polylog n or closer to square root of log n? Yeah, that's exactly as I said, something I have no idea eventually what the answer is, right? And it's possible that like developing better local exploration algorithms for matchings would perhaps lead to, or like sparsification would perhaps lead to better MPC algorithms. Yeah, there is some not very formal connection there, I think, but yeah, I don't know what in the end what the answer is.
Okay, so Yannic was asking, do you think that MPC is the right model to look at?
A good question. So yeah, for synchronous computation, I think it is the right model to look at. There are some other things that some people have been developing. Like there is this AMPC, which is like, so there's this thing called the big, what's called the big table. And so you can do some, basically it's adaptive MPC. And so there is a recent paper on, I think, arXiv from some people at Google who actually ran tests and they claim it works very well. So perhaps this is something that, it also allows for solving some problems more efficiently. So maybe, this is something that would also be practical, but, it's harder to have an opinion on that without running the experiments oneself.
Yeah, so sorry for cutting the line, but
sure.
just follow up to this thing. This AMPC was this merger of local computation algorithms and MPC, right? So you can like query a weird shape.
Right.
Okay. All right. And then Krzysztof Lenzen was asking, wouldn't it be straightforward to run a synchronizer? And there's a constant depth 3 would just incur a constant factor round overhead. So I guess it was like synchronizing the asynchronous computation in MPC. Oh,
I see. I see. So like a 3 is basically like an adaptive. Yeah, I don't know. Maybe. Yeah, it's a good question. I mean, because like we don't really even have a good model for asynchronous computation, right? So just to deciding what the model should be would be a good starting point to showing that maybe it's just the same thing.
Okay, and then Michael was asking if it's interesting to study the communication required by these algorithms and to minimize it, or is round complexity the only thing that we care about?
Yes, so the round complexity has the problem that essentially everything can be reshuffled between every round, right? So then the communication becomes the total space, in the worst case, at least the total space times the number of rounds, which can be a lot. So definitely if you could develop algorithms where not all of the data has to be reshuffled in every round, that could be interesting, right? There hasn't been much research as far as I know on that. So that's definitely an interesting question. And like many of these things that I discuss here, they totally take advantage of the fact that you can reshuffle everything in every round. Like there is not that much of a limit on how much each machine can send and receive in every communication round.
Okay, and then Janne was asking, what are your views on MPC versus congested click and the K machine model and BSP and other fully connected models with space limitations, local space limitations?
Sure. Yeah, I mean, so there is a few things, right? Congested click, I guess with some restrictions, it can be shown that this is very close to MPC with near linear space, right? So this has been shown. We were, for instance, when I was writing, with other people, this paper on near linear space regime, we were not aware that there is this connection, but apparently it is. So our algorithm also implied something for congested click. K machine BSP. Yeah, so there is a number of models. So MPC can be also seen as like a specific instantiation of BSP to some extent, with some setting of parameters, because BSP is very generic, right? Like there can be like multiple levels of hierarchy, and machines can talk across them. So yeah, I mean, so the advantage of this is that it's basically MapReduce, and some of these other systems is something that people use in practice, right? So this is like a specific setting of parameters that is actually interesting from the practical point of view, and you don't have to solve it for all possible settings of parameters. It's just a specific range of parameters that is worth focusing on due to the practical interest. Yeah. BSP, yeah, what is BSP? It's bulk synchronous parallel. So it's a model that was introduced by Les Valiant at some point. Yeah, I think this information should be enough to look up more information about it.
What do you think about applying kind of translating actually the theoretical models into practice, like MPC, as there are some problems, like we have a number of the machines in theory, and in practice there are like clusters of machines, and they have kind of like gigabytes of memory, and with many cores, and many like graph data sets, like for open data sets of Stanford SNAP data sets are too small, like like tens of megabytes. And yeah, and we are saying that it should kind of be exceed the size of like machine. I mean I mean memory. So yeah, how we have to kind of translate those to practice actually.
Yes, I mean, so definitely for running experiments, it's like a general problem with any type of big data research is that there isn't that much data out there in some sense, given the power of like single machines that we have. So on the other hand, like even at IBM, working with some external customers who wanted to solve something, some big problems on the data they had, and they had like really rich data, right? Then those types of data sets do exist, right? It's not they are not necessarily publicly available, and And of course, like even for those data sets, you can ask, maybe just sampling from it down to something that fits onto a single machine would be enough in practice. Maybe it would perform just as well, right? So that's definitely a problem for like running experiments and in practice. Like, I mean, other ways of bringing it to like practices, just implementing things and just, open sourcing them so that side is kind of not affected directly by the sizes of the data sets that you see, publicly available data sets, right? So, yeah, so I mean, so that's definitely like something to think of. I mean, in the end, those systems do exist for a reason, right? People do have big data sets, so it's just not so easy to get your hands on unless you are at a company that actually has those data sets, and often it's like a relatively private data, so it's not so easy to share with the public.
What do you think about generating data sets? Is it valuable to generate data sets or not?
Yeah, I mean, so it depends how it's generated, right? If it's like, say a random Erdős-Renyi graph, then, for some things we already know the answer without looking at the data set, right? So it also depends on how reasonable the data set you generate is, right? Like what are the reasons you generate it and how you generate it. Sometimes also there are better algorithms under some assumptions about, say, the density of the graph or the structure, right? So once you make those assumptions, then weaker assumptions, right? And you showed that your algorithm works well under those assumptions, like, there has been some research on, say, power law graphs and whatnot, then, this is more likely to match, I guess, what people might be dealing with in practice.
We will give the turn next to Slobodan. Slobodan is a postdoc at MIT working with Ronit Ruppinfeld. He has done a lot of research in sublinear algorithms and also applications in things like machine learning from clustering.
Thank you for the introduction. I would first of all like to thank the organizers for giving me the opportunity to speak here. I truly like topics and problems discussed in ADGA, so it's my great pleasure to be part of it today. Thanks a lot. So today, as Yaila said, I will talk about local computation algorithms, which are a type of sublinear algorithms. And I would like to start with two motivating examples that hopefully will convince you that these type of algorithms are around us much more than it might seem on the first sight. So the first example is navigating through cities. So imagine that you have a map of Freiburg, and you want to go between Freiburg Minster to Freiburg Martinstor. So what you would probably do is find these two places on the map, then scan neighboring streets from one place to another one, and then eventually come up with some route that feels to be short enough. And you would take this one and take a walk between these two places, right? And again, I believe that this is something that we do almost on a daily basis. Here is another example, which is about file decompression. Imagine now that you have an archive of images, quite large, let's say 5 gigabytes. But unfortunately, you didn't give a proper name to this archive, so you just called it images.rar. So the name itself is not very meaningful. Now it's even worse. When you open this, when you just look at the files which are inside, you see a bunch of numbers. So you don't know what these images are about. What they would usually do in this case is, well, they would open a couple of images. They would see what's on them and try to infer from these couple of samples what is inside this archive. And it's very important here that most likely you will not first decompress the entire file and then look at the images, but rather do decompression on file basis, right? And interestingly, there was also a lot of theoretical work trying to understand how efficiently we can do the compression of only a couple of files without having to decompress, without having to to decompress the whole array of documents which are inside. So the question is, what is in common these two examples, right? And here are a couple of things that I would like to point out. So the first one is that in both cases, we inspected only small parts of the entire structure, right? When we looked for a short path between these two places in Freiburg, we didn't look at the entire map, but mainly locally at the streets connecting these two places. And similarly, in the case of images, right, the program, the algorithm, which is on top of it, it has some tables, some data structures, and scans only parts of these structures in order to perform the compression of one or two files. The second very important property is that these two operations are consistent. And this is a very important property of local computation algorithms. And let me clarify in the context of these two examples. So for instance, if you would start asking the questions, okay, what is image 9, what is image 10, and so on, eventually you would be able to reconstruct, to decompress the entire file, image by image. And this is what we mean consistent in this case, right? What you are getting actually makes sense. And similarly, in the context of maps, if you would ask for a shortest or for a short path between any 2 points on the map, you'll be able to reconstruct the full map. And finally, we get, this is a bit subtle here, but we have access to some simple and easy access to this object, right? We are able to traverse these objects very quickly from one point to another point, at least locally. So speaking in terms of algorithms, the first property talks about complexity. And the second property says that the algorithm is meaningful. And we will see one more comment about this in a couple of slides. And the third property says that we have some probing access to these objects that we care about. And there is one more property, which is probably the most important here, is that in both of these problems, there is some output which is potentially large, which actually in these two cases is huge, right? In the left example, we have 5 gigabytes of images. On the right example, we can think that there is OP shortest paths, some are hidden, but what we would like to learn is only a tiny part of this potentially huge output. And this is what local computation algorithms are about, right? Their goal is to learn only small parts of outputs. And this was introduced by this set of authors in 2000, roughly 10 years ago. And so slightly more formally, right, there is we think of the whole setting behind LCA is that there is a huge output. There is some function f that acts on this there is a huge input. There is some function f that acts on this input. And this function f essentially defines some output, right? It's written somewhere. We don't have it. We don't have full access to this output, but it exists. What you would like to do is to learn only a tiny bit of this output by ideally looking at only very small part of the input. And again, very formally, what we can do about this input is to ask for the ith bit. Okay? And now I will mention this, go over some of the properties of LCA, and as running examples, I will take approximating maximum matchings. And in fact, in the rest of the full presentation, it talks about approximating maximum matchings and some techniques for designing efficient algorithms for this problem. So just as a brief reminder, I would like to emphasize that this is about approximating maximum matchings. So in particular, we would like to choose, given the graph G, right, the goal of this problem is to choose a set of non-overlapping, choose a set of disjoint edges, and such a set which is not much smaller than the maximum possible set, right? For instance, in this case, approximate maximum matching are these three edges. And if you don't include this one, it is still okay because we don't care about getting maximum one. Okay, so this is example that we should have in mind for the rest of this presentation. I will now go back to these properties that we mentioned in the context of LCA and just relate them to matchings. Okay, so the first property, or the first two properties are what we mean actually by these probes to the input, and how is then a complexity defined. So the type of access we would like to have to this input graph, and again, think of this input graph as being something very huge, something that we don't want to keep in the memory, but there is a data structure on top of this graph that enables us to actually access to this graph. And the type of access that we have is to ask what is the jth neighbor of a given vertex I. Okay, so this is type of questions that we can ask about our graph, and then this naturally defines the complexity, the efficiency of the algorithm which is using this type of questions, which is simply the number of probes, the number of these questions that we ask in order to get an answer. For instance, the answer can be whether an edge is matched or not. Okay, and I would like now to get back to this consistency property, and for that, let us start by what we like to learn. So as we said, we, for instance, would like to learn whether edge E is matched or not. Now, here is a simple answer that you can give. Well, for every edge in the graph, there is a matching that contains this edge. So in principle, you could always answer yes, right? Because there is some hidden matching which contains this graph. And this is very important part of consistency, that a priori, before even we start the algorithm, we want to fix some matching. And then for this fixed matching, which is now, we think of this as a fixed output, for this output, we would like to answer queries whether edge is matched or not. Right, so if, for instance, for this edge, we say that yes, it is matched, then for this edge E2, even though the question whether this edge E2 is matched or not is oblivious to whether we ask query about edge E1 or not, the answer should be no. Okay. So this is again very important property when it comes to LCA to keep in mind. Otherwise, for many problems, this question is trivial and in fact not very interesting and not very meaningful. And so now we can define the LCA as a way of consistently answering queries, for instance, whether something is in the matching or not, via a small number of probes to the structure or to the inputs. And what we usually would like to do is to use small space. Okay, good. So this is a definition of LCA. And so before I mention some results for matching, let me also mention that we will use delta to refer to maximum degree of a graph. And kind of usual assumption is this delta is much, much smaller than the graph size and the number of vertices. And in fact, for many problems, it is very interesting to come up with results which are very efficient even when delta is polynomial in N, let's say small polynomial in N. Good. So this is a subset of results for LCA algorithms for approximately maximum matchings. So one of the first algorithms had exponential dependence on maximum degree on delta. And then there was a sequence of results which eventually gave us only linear dependence on maximum degree. There, in some of these results, there are also Logan factors, which I'm not mentioning here. Let me also mention that the way some of these results are stated in the paper, they're in terms of expected complexity. But what I'm showing here is the worst case complexity in terms of number of probes that we need to approximate maximum matching. And just one more thing to add about, again, this result is that many of these are not only about matchings, but similar techniques also can be used to get results for MIS and set cover, as many of these papers illustrate. Good. So these are already of results for matchings. What is presented in the full talk is the first one and the last two. The main ideas how to get this probe complexity. In general, LCA was studied in the context of graph algorithms quite a lot, and here is only some number of results. Right, in addition to matchings, again, MIS, vertex cover, graph coloring. These are all very interesting problems that people are interested in, and they have various techniques that lead to efficient algorithms. But what is the outline of the full video? And I would invite you to actually have a look at the full video to see discussion about these techniques. Is that the full video starts first with introduction with describing the peeling algorithm. This is a general approach for constructing matchings, regardless of LCA. Then the full video describes 3 techniques for simulating this peeling approach. Now, in this presentation, I will not talk about these techniques, but I will only describe this peeling algorithm. And in fact, if there is anything to be taken and remember from this presentation, I think that this is precisely at least this approach, because it has been used in many different settings, in distributed computation, parallel computation. Even Krzysztof in his talk also referred to this peeling approach. It has been used in streaming setting, LCA. So this is very robust. This is very robust approach and something to keep in mind if working with matchings. So let us see what this peeling algorithm does. On a very high level, this approach tries to take care first of or to peel off vertices that have highest degree, vertices that have degree between, say, delta over 2 and delta. After doing that, then the algorithm proceeds with the rest of the graph. Well, now the remaining degree, maximum degree of the remaining graph gets halved. Okay, so the algorithm proceeds in log delta iterations. In every iteration, it defines let H be the vertices that have degree, which are at least vertices that have degree at least delta divided by 2 to the I. So in the very starting iterations, those are vertices that have degree between delta over 2 and delta. And then let us look at the example on the right. What the algorithm does is that every vertex in H, which stands for high degree vertices, every vertex in H marks one of its incident edges uniformly at random. For instance, we get this marking. Now, in the third step, we add to the matching edges, these marked edges, which are disjoint from the other marked ones. Like in this example, only this edge among the 3 marked ones, only this edge E will be added to the matching. Okay, so it will become part of our output. And then as the final step of one iteration, the algorithm removes all meshed vertices. It will remove these 2, but it also removes all non-meshed vertices which are in H. Okay, and the remaining graph would be like this. And one can show that this very simple approach gives you a constant factor approximate maximum matching. And moreover, it is robust in the sense that there are several different variants to choose incident edges on these vertices in H. Also, this constant 2 is not very important. It can be any constant. And so in general, this algorithm, it's simple itself, but again, very robust for and nice for small changes. And it was introduced in the context of parallel RAM algorithms in the 80s, but has been changed and has been modified many times and used different variants, again in dynamic setting, streaming setting, and parallel computation. Okay, so this would be this is the peeling approach, and then again I would invite you to have a look at the full video and see how in fact this can be simulated in LCA and even give you complexity that in roughly delta many probes to the graph can tell you whether fixed edge, whether given edge is in imaging or not. Okay. So before I conclude, let me mention some open questions. So all of this was mainly about matchings. So these results give you only approximate maximum matching. It does not give you the final bound that has linear complexity on delta in the number of probes. It doesn't give maximal matching. It would be nice to get maximal matching also in the same probe complexity, even in the worst case. And besides matching, there are many other interesting problems. MIS, for instance, it seems to be very challenging. The best upper bound that we have so far is delta to the log delta probe complexity by Ghaffari and Yarovito. It would be quite nice to get MIS in only poly delta times log n many probe complexity. Set cover is another very interesting instance for which we have round complexity, which is delta to the log delta times log delta, so much higher than what we know for MIS and maximal matching. So as I managed to convince you, LCA are all around us. So it would be quite cool to come up with new techniques for known problem and also to find other interesting problems. And finally, something that I would like to mention, very often when we are faced with big structures, with large structures, they're not static, they're dynamic, they change over time. So it would be interesting to design LCA algorithms that can accommodate these changes and perhaps be more efficient when you try to recompute something in the same region of the graph after you perform computation before some update. By this, I will conclude, and thank you.
Why do you have the log n factor in the open question? And couldn't you have something like a function of delta plus log star n complexities, like in the local model?
Yeah, that's a great question. So the reason why I added times log n is kind of to emphasize that getting given to delta for maximal matching is open. But yes, that's a great question, whether at all this multiplicative is needed, whether we can first of all make it additive and then potentially even improve this additive log n to something which is even more efficient. The reason why in some of these results we get log n is to get with high probability statements. But again, there is no obvious reason or an evidence that this is actually needed. That's a great point.
Also, there is this shattering business, right, that you get with this polylog n factor. that you basically first do something and then you have a shattered graph and then you do something else. So I'm not sure if it's only to get the with high probability thing, but you also have this two-phase thing. And I mean, this also makes the additive thing a bit annoying because you have to like simulate the whole thing on all the nodes.
Yeah, that's right. That's the reason why many of the results have this log n, right? Like your result are and some others.
Yeah. Actually, Yannic once also kind of pondered about. Sorry for stealing the stage, but I just thought that like Yannic mentioned once that there's this inherent feature in the LCAs that like if you run first algorithm 1 and then algorithm 2, it often becomes this multiplicative thing, because you need to like simulate the first round for every node that your behavior you want to know. So you don't get this plus, but you always tend to get this multiplicative factor there. Not sure if that says that it's mandatory, but it just feels a bit like that.
Yeah, the one question, what is the intuition behind the proof of constant approximation of the billing algorithm? One way to think about this is, so if you think only about high degree vertices, right? So the first question is whether you can really, by choosing random edges and by resolving conflicts in a trivial way, whether you can get something useful. Maybe think of fractional matching first, right? So every high degree vertex would add fractional matching of 1 over delta on one of its edges. And then it would round it by choosing one of the edges, it would round this fractional matching to integrand immediately. Now, if you look at fractional matching, it's clear that it's still a matching and that you are indeed matching, that you are indeed adding to the matching a large fraction of high degree vertices. So now this is only a question of rounding immediately this fractional matching, even in the first stage, and then you repeat this process. And one can show that when you round this and resolve conflicts in this very simple way, then it in fact preserves constant fraction of matched edges to what fractional matching will give you. Are there some gap results similar to local model for some graph classes? Oh, yeah, very good question. Not that I'm aware of. When you say gap results, you mean lower bounds and upper bounds where we don't have tight results, or?
I meant also some like the speed up results.
Oh, I see. Not that I'm aware of. Yeah, but that's a very interesting question. Whether we can get these general type of reductions, which would say if you solve something for this class of problems, then you immediately get for the whole class, right? And that's a very interesting question.
I have a question.
Yes, please.
What do we know about lower bounds? I guess lower bounds from the local model should carry over, but they seem very weak. So do we know anything beyond that?
Again, at least when it comes to graph problems, not that I'm aware of. As you said, exactly, like we can, we know that from local we can carry this, but that's the best that I'm aware of, at least for graph problems.
Okay, and then Dennis was asking, doesn't an LCA imply something to the local model and vice versa? So there should be some sort of a gap from the local gaps.
Yeah. So if you have a local algorithm that that runs in, say, R rounds, then it's kind of direct to simulate this local algorithm in delta to the R many probes. Right. So this is just the direct bound that you get in one direction. Now, when it comes to the other direction, if you look at the LCA approach, and it is tuned to exactly number of probes that you need to look at locally, but it also makes certain radius. Now, if you would know what is the radius of your approach, you could transform it directly to local. many of these approaches that I discussed, they don't because they simulate this pinning approach. Let's say in matching, for instance, you have this radius of computation, but there are some other approaches when it comes to shattering techniques that don't have so small, at least not probably so small radius. So maybe if you would take them to local computation, you would need to pay kind of more in terms of round complexity in local computation. But it's very nice for LCA that you can make very long path. Let's say it's even root delta, very long path by paying very little for the probe complexity. And then this type of approach, definitely wouldn't be something which you consider efficient in local computation, because you need to go all the way root delta steps away, which is usually not so efficient for this type of problems in local. Yannic, just to reply to your question, that's really great question. Yeah, I mean, people can leave, right? So this is really great question. So for instance, if you wouldn't care about total memory in LCA, for matchings, just as an example, or MIS, you could simulate greedy algorithm, right? Whenever I ask you about some query, if I ask you about the very first edge or very first vertex, you say, yes, it's an MIS. And then you mark all the neighboring edges or all the neighboring vertices, and you store that they are marked. Now, when I next time ask you if you're already marked, then you say, I'm not in MIS. If you're not marked, you say, oh, I'm in MIS, and you mark all your neighbors. So in general, if you allow for lots of memory, then at least for MIS, matching, set cover, you could simulate standard greedy algorithms pretty much directly.
I guess there's one issue somehow. Mm-hmm. The way I understood Ronit talking about this, one should maybe think, I guess one should think of different queries being able to take part in parallel, and then you have some issues with this kind of approach, even if you have the memory, right?
You're right. That's another nice feature that you can get by simulating this fixed output. Yes, you're right. You're right. Shared randomness from the results I'm aware of is quite important. It's quite important to, so these results that I'm at least mentioning in the long video and many others, they are randomized results. And in order to have consistent output, you would like to have shared randomness. Good thing is that that randomness that you need doesn't require some large independence. So in fact, you can design small size hash functions, polylog and size hash functions, and then you can use them. Right, every vertex would just have access to randomness via this hash function, and then we would use it. But then it would be consistent for the entire output. So this seems to be very important for many of the known results. If you would take that away, the results would probably break. Great point. You don't. You use for hashing, but other than that, not. You need to remember your exploration tree, but this is kind of local memory, right? Not something that you need globally.
Next speaker is Faith, and she's a professor at University of Toronto, has many great publications, and for example, a lot in shared memory. And I guess that this talk is not about shared memory, but something totally different. And as the title suggests, some labeling schemes for radio networks, but I don't want to take any glory from your talk, but I want to give the microphone to you so you can give the talk.
Okay, thanks. Yeah, Okay, in this talk, I'm primarily going to be discussing work I did over the past couple of years with Avery Miller, Barun Gorain, Andre Pelk, and Seth Gilbert. The model of computation is a fixed topology network with n nodes. It's synchronous with time divided into slots, and each time slot a node can decide whether or not to transmit. If it does not transmit, but exactly one of its neighbors does transmit, it receives the message that neighbor sent. If two or more neighbors of the node transmit in the same slot, then there's a collision and the node does not receive anything. In the figure, there are two nodes that are transmitting. The two nodes in orange receive the message from the top transmitting node. The other two white nodes receive nothing. The left one because two of its neighbors are transmitting, and the right one because it's the only neighbor. Its only neighbor is not transmitting. In the radio broadcast problem, the network contains one node called the source that knows the message M. The goal is to ensure that all nodes eventually know M. The same algorithm is used by each node to determine when it should transmit. This can depend on the history of the node. For example, if the node has not yet received M, it should not transmit. Deterministic radio broadcast means that the algorithm used by nodes to determine when to transmit is deterministic. If the nodes have no identifiers, there are networks, for example, a 4-cycle, in which deterministic radio broadcast is impossible. When the source transmits the message M, both neighbors of the source receive the message. In each subsequent slot, they both transmit or neither transmits, since they are performing the same algorithm and have the same history. In either case, the remaining node does not receive the message. If each node has a distinct log n bit identifier or label, then a round-robin schedule completes with an O of d n slots, where d is the source eccentricity. This is the maximum distance from the source to any node. In the network illustrated here, d is equal to 2. A deterministic radio broadcast algorithm consists of two parts: a labeling scheme, which assigns a label to each node of a network, and a transmission protocol, which enables each node to decide, based on its label and its history so far, whether to transmit, and if so, what to transmit. The first interesting deterministic radio broadcast algorithm was published by Klamtak and Weinstein in 1991. They gave an O of log squared n algorithm for networks with source eccentricity 2, and then used this algorithm one level at a time to get an O of d log squared n algorithm for networks with source eccentricity d. Their algorithm assumes that nodes have distinct identifiers. Over the next 16 years, there was a series of increasingly faster deterministic radio broadcast algorithms, culminating in an algorithm by Kowalski and Pelk, which uses d plus O of log squared n slots for networks with source eccentricity d. Their algorithm is as fast as possible, matching a lower bound by Allon, Barnoy, Lineal, and Peleg from 1991, which says that there are networks with source eccentricity d for which omega of d plus log squared n slots are necessary. A year ago, Gorain, Miller, Pelk, and I showed that 2-bit labels are sufficient to perform deterministic radio broadcast for any network. Like the algorithms on the previous slide, the label of each node is carefully chosen based on knowledge of the entire network. The broadcast always completes within 2n-3 slots, and there are networks for which 2n-3 slots are used. This year, Gilbert and I gave a deterministic radio broadcast algorithm using 4 bits for each label, which completes with an O of square root of nd slots, which is faster when d is little o of n. Then we defined the class of continuous broadcast algorithms, which include both these algorithms, and proved that any algorithm in this class requires omega of square root of nd slots for some network. In other words, our algorithm is optimal in this class. There's more about this lower bound in the longer version of the talk. We also came up with a different algorithm that is not in this class. It uses only 3-bit labels and completes an O of d log n plus log squared n slots. This is better than any continuous broadcast algorithm if the source eccentricity d is little o of n divided by log squared n. The problem with this algorithm is that it is non-constructive. We rely on the probabilistic method to show that for any network, there's a good choice for the 3-bit labels on its nodes. Finally, we give another algorithm with 3-bit labels that takes slightly longer, but there's a deterministic algorithm for constructing the label of each node in the network. I'll begin by presenting the algorithm from 2019, but before that I need a couple of definitions. A set of nodes X is said to be a dominating set for a set of nodes Y if every node in Y has a neighbor that's an X. For example, in the first and second networks, the set of brown nodes is a dominating set for the set of orange nodes. However, this is not true in the third network, since the middle orange node has no brown neighbor. X is a minimal dominating set for Y if it is a dominating set for Y, and no proper subset of X is a dominating set for Y. For example, in the second network, the set of brown nodes is a minimal dominating set for the set of orange nodes, but in the first network, the set of brown nodes is not a minimal dominating set for the set of orange nodes. Why are minimal dominating sets useful for radio broadcasts? Well, they have the following nice property. Suppose that X is a minimal dominating set for Y, and all nodes in X know the source message. Now consider a slot in which only the nodes in X transmit, and they all transmit the source message. Then for each node U and X, there's some node V and Y that receives the source message from U. Node V is called a private neighbor of node U. For example, the top two orange nodes are private neighbors of the top brown node, and the bottom orange node is a private neighbor of the bottom brown node. In the dominating set mechanism, each node has a label consisting of 2 bits, which are called the join bit and the stay bit. Slots are grouped into 2 rounds with 2 slots each: a dominator slot and a feedback slot. At the beginning of each round R, 3 sets of nodes are defined. Informed is the set of nodes that know the source message. Frontier is the set of nodes that don't know the source message but have at least one neighbor that does. Finally, DOM is a subset of the informed nodes that is a minimal dominating set for the frontier nodes. In the dominator slot, each node in DOM transmits the source message. Each node in the frontier that receives the source message in this slot is said to be newly informed. It joins the minimal dominating set for the next round if and only if its join bit is 1. Each node in DOM has at least one newly informed private neighbor in the frontier. One such node is chosen to be its designated feedback node. If the stay bit of a node in the frontier is 1, then it transmits 1 in the following feedback slot. A node in DOM stays in the dominating set for the next round if and only if it receives a 1 from its designated feedback node in the feedback slot. The join and stay bits can be constructed by simulating the algorithm 1 round at a time and using a greedy algorithm to construct a minimal dominating set for the round. For example, in the first round, the minimal dominating set consists of the source, and the frontier consists of its neighbors. Each node in the frontier receives the message. They all have stay bit 0, so they don't transmit in the feedback slot, and the source leaves the dominating set. The top 2 orange nodes have join bit 1, so they join the dominating set. In the second round, the two brown nodes are in the dominating set, and they transmit the source message in the dominator slot. The 3 orange nodes constitute the frontier, and 2 of these nodes receive the source message. The top orange node has stay bit 1, so it transmits in the feedback slot. It is the designated feedback node for the top brown node, so the top brown node stays in the minimal dominating set. The top orange node also has join bit 1, so it joins the minimal dominating set. The designated feedback node for the other brown node is the bottom orange node, which has stay bit 0 and join bit 0. Hence, neither of these 2 nodes are in the new minimal dominating set for round 3. In the third round, the 2 brown nodes at the top are the dominating set, and they transmit the source message in the dominator slot. The 2 orange nodes in the frontier both receive the source message in the dominator slot, and both have their stay and join bits equal to 0 since the broadcast is complete. In the level dominating set mechanism, we basically have a modification of the dominating set mechanism. It makes use of the level of each node, which is its distance from the source. For example, in this network, the nodes in the brown circle are in level 1, the nodes in the orange circle are in level 2, and the node in the yellow circle is in level 3. It follows from breadth first search that the neighbors of a node in level L are in levels L-1, L, or L+1. First, let's consider the special case when the source eccentricity is 2. In round 1, the dominating set consists of the source, and the frontier consists of the nodes in level 1. In subsequent rounds, the frontier is contained in level 2, and we choose the dominating set to be contained in level 1. We can show that the dominating set mechanism completes in 1 plus the minimum of the size of level 1 and the square root of 2 times the size of level 2. And this is all together is O of square root of n. In the general case, in order to keep the levels separate, there are 2 additional bits in the label of each node, which are used to record its level mod 3. When a node transmits the source message M, it also sends its level mod 3. This enables a node that receives the message to determine whether it comes from the same level as itself, one earlier level, or one later level. To make the algorithm behave like the source eccentricity 2 case, a node in the frontier ignores a message containing M unless it comes from the level immediately before it. The labeling algorithm also ensures that the subset of DOM at some level L-1 is a minimal dominating set for the part of the frontier at the next level L. To prevent interference between different levels, only nodes and levels that are multiples of 3 apart can transmit in the same slot. Since there are D levels excluding the source, and it takes O of square root of n rounds for one level, it's easy to see that O of D square root of n rounds suffice. With a more careful analysis, we're able to show an O of square root of nd round upper bound. To get faster algorithms, we start with the dominating set mechanism, but add one more bit and one more slot. The new bit is called the go bit, and the new slot is called the propagation slot. The propagation mechanism behaves the same as the dominating set mechanism in the dominator slot. Namely, each node in the dominating set transmits the source message. The only difference in the feedback slot is that each designated feedback node transmits its go bit as well as its stay bit. A node in the dominating set transmits the source message in the propagation slot if it received a go bit with value 1 from its designated feedback node in the feedback slot. Otherwise, it does not transmit during the propagation slot. The join and stay bits are constructed as in the dominating set mechanism by simulating the algorithm. However, the go bits are constructed probabilistically prior to running the algorithm. For each round R, a random value P between 1 and log n is chosen, and the go bit of each designated feedback node in round R is chosen to be 1 with probability 1 over 2 to the P. First, we prove that if node V is in the frontier, then V receives the source message in the propagation slot with probability O of 1 over log n. Then, by a Chernoff bound, there's a high probability that any particular node in level L knows the source message within O of L log n plus log squared n rounds. Finally, by a union bound with high probability, every node knows the source message within O of D log n plus log squared n rounds. Hence, by the probabilistic method, for any network, there exists a choice for all the go bits so that the propagation mechanism completes with an O of D log n plus log squared n rounds. Thus, our algorithm, which uses only 3-bit labels, runs almost as fast as the best deterministic radio broadcast algorithm, which uses large labels. To construct the go bits deterministically, we rely on the following lemma from Klamtak and Weinstein's paper about connected bipartite graphs with parts x and y. The lemma says that there is an efficient algorithm to compute a subset x prime of x and a reasonably large subset y prime of y, such that each node in y prime has exactly one neighbor in x prime. They use this lemma to obtain an algorithm that completes with an O of D log squared n slots using nodes with distinct identifiers. We use the same lemma, but we apply it to different sets x and y. Specifically, in each round R, Y is the set of all uninformed nodes in the smallest level L that contains uninformed nodes, and X is the subset of the nodes in the minimal dominating set for round R that occur in level L-1. We are able to prove that once every node in some level knows the source message, every node in the next level knows the source message within 15 log squared n more rounds. Since each round consists of 3 slots, the propagation mechanism completes with an O of D log squared n slots, where D is the source eccentricity. We've shown that for any network, there exists a choice for the go bit so that every node knows the source message within O of D log n plus log squared n slots. And there's a deterministic method to construct the go bits so that every node knows the source message within O of D log squared n slots. So it's just a little slower. An open question that remains is the existence of a deterministic radio broadcast algorithm using a constant number of bits for the label of each node, which completes an O of D plus log squared n slots, matching the lower bound for arbitrarily large labels. For some families of networks, it's possible to perform deterministic radio broadcast using smaller labels. For example, in trees, labels are not needed. Each process simply transmits a source message in the slot after it first receives it. The structure of the network ensures there are no conflicts. In networks with source eccentricity 1, the source directly transmits the message M to all other nodes, so deterministic radio broadcast can also be performed without labels. In networks with source eccentricity 2, a slight variant of the level dominating set mechanism works using 1-bit labels. The source successfully transmits to all its neighbors in the first round, so it doesn't stay in the dominating set. Hence, the stay bits of all nodes in level 1 are 0. Nodes in level 2 never transmit, so their join bits are all 0. If the source transmits M0 and nodes in level 1 transmit M1, a node learns its level when it first receives M. Thus, only 1-bit labels are needed. Notice that the label has a different meaning for nodes in level 1 and nodes in level 2. For nodes in level 1, its label is its join bit, and for nodes in level 2, its label is its stay bit. Earlier this year, another family of networks was defined for which deterministic radio broadcasts can be performed using 1-bit labels. A network is level separable if, for every level except the last level and the level consisting of the source, the nodes in that level can be partitioned into 2 parts, here colored red and brown, so that every node in the next level has exactly 1 red neighbor or exactly 1 brown neighbor. In this example of a level separable network, the top 3 orange nodes each have 1 red neighbor, and the bottom orange node has 1 brown neighbor. In the first slot, the source transmits. In the next slot, the red nodes in level 1 transmit. And in the following slot, the brown nodes in level 1 transmit. This ensures that all nodes in level 2 are informed. If the source eccentricity is greater than 2, then in the next round, which consists of 2 slots, the nodes in level 2 transmit 1 part at a time. This continues 1 level per round until the nodes in level D are informed. Since 2-bit labels are sufficient for deterministic radio broadcasts in any network, and deterministic radio broadcast is impossible without labels in a cycle of length 4, a question that remains is whether 1-bit labels are sufficient for deterministic radio broadcasts in any network. If not, it would be nice to characterize the family of networks for which 1-bit labels suffice. An extension of deterministic radio broadcast is acknowledged broadcast, where the source receives an acknowledgement message in some slot after all nodes receive M. Acknowledged broadcast can be accomplished using 1 additional bit per label. To label the nodes in the network, first simulate the deterministic radio broadcast algorithm to get the join and stay bits. Then choose a node Z that is informed last and set its extra bit to 1. Note that its join and stay bits are both 0. Next, choose some shortest path between the source and Z, in which the nodes in between the source and Z all have join bit 1. This is possible since the nodes with join bit 1 are the only nodes besides the source that transmit M. The extra bits of the nodes on this path are set to 1. The extra bits of all nodes not on this path are set to 0. The first part of the transmission protocol is the same as the dominating set mechanism or level dominating set mechanism. When node Z first receives the source message, it transmits an acknowledgement in the next slot. It is the only node with join bit 0 and extra bit 1. When a node with join bit 1 and extra bit 1 first receives an acknowledgement, it forwards that acknowledgement in the next slot. The acknowledgement travels along the chosen path, 1 node per slot without conflicts until it reaches the source. What happens if the nodes of the network are labeled before the source is chosen? In this case, a variant of acknowledged broadcast can be used. The idea is that the labeling is done using a node with smallest eccentricity as a surrogate source. During the broadcast algorithm, the surrogate source broadcasts a request for a message. The actual source acknowledges with the source message M instead of Z, and then the surrogate source broadcasts M on its behalf. There are some additional important details which I haven't mentioned, but which can be found in the longer version of this talk. An open question that remains is whether an extra bit is needed for acknowledged broadcast or for broadcast from an arbitrary source. Finally, suppose that nodes can detect conflicts. This means that if 2 or more neighbors of a node transmit in the same slot, the node receives a special conflict message instead of receiving nothing. Can broadcast, acknowledged broadcast, or broadcast from an arbitrary source be performed using smaller labels or fewer slots in this model? Thanks a lot, and I'm happy to answer questions.
Maybe I can start by asking, for the last open question you mentioned, like what is known? Somehow it feels like this conflict resolution should make a difference, but do you know like something about it?
No, I don't.
Okay, that's cool. That's the best answer, I guess.
Yes, so it's a good open question. It's not clear how it's going to help necessarily, because you are actually not transmitting the, you aren't actually, the source message isn't actually being received. It may help a little bit somehow in feedbacks, in the feedback slot, but I'm not sure how to do that. And I have no idea how this can help.
Yeah, I'm also not saying that I know how to use it. It just feels like it makes a big difference. But if it feels to me like it makes a difference, that really doesn't mean that it makes a difference.
No.
Okay, then there was Avery Miller was asking, is there an intuitive way of thinking about the go bits and how broadcast becomes so much faster?
Essentially, what the go bits are doing is simulating the decay algorithm. So that's a randomized algorithm that some of you may have heard of that basically processes randomly flipped coins and decide to broadcast. And it has good behavior for doing things like broadcast. And that's essentially what the go bits are trying to simulate. That's the best intuition I can give. It really relies, and that was our motivation really for looking at it. We were really trying to do something like the decay algorithm, and it has some similar flavor to the decay algorithm.
I have a question, maybe a suggestion. There is another version of broadcast, which is long-term or ongoing broadcast, in which pipelines, in which there is again a root, a broadcasting node, but the idea is that in every slot it can broadcast some bounded amount, like in the congest case. And the advantage is that after it is done, transferring the message, the first message to its neighborhood, near neighborhood, the message is being carried further by additional nodes, and this node is already transmitting the second message, and so on in pipeline. So there has been some work on that. Actually, it's predated the algorithm of Orly from Touch. And the question is, can reducing the label size be applied also? I assume you will not have an immediate answer, but I think it might be an interesting question.
So what you're saying is that if we had pipeline broadcast, that maybe we could amortize the cost of, or having done it once, then you then have a pathway, is it in the same sense as you sort of have like a minimum spanning tree built, and then you could just do the broadcast directly that way.
Yes.
Yeah. Perhaps, I'm not sure. I suppose that one would get, I mean, there is a spanning tree. Well, I don't guess it doesn't have to be minimal, but there is a spanning tree that I guess is created if every node takes as a parent the node from which it first received the message M.
For example, maybe you don't necessarily need to, it might not even need to be the same spanning tree, because you might not need to minimize the time that the delay of the first message to arrive everywhere. You want to, in such a problem, you want to, the question is the throughput.
The question is what? Pardon, I'm having trouble hearing you.
The throughput.
Oh, the throughput, yeah. It hasn't been something.
Microphone is not good.
Yeah, no problem. Okay. Yes, I mean, I think those are interesting questions and good directions to look at. Thanks for the suggestion.
So Dennis said that he read the 2019 paper and liked it. And he said that if he remembers correctly, it uses 2 bits and there's a lower bound of 1 bit. And what do you think is the right answer?
I don't know. I mean, that really is one of the open questions. I know that Avery is sort of believes in that 1 bit's the right answer. My inclination would probably be 2, but not based on anything but, you know, gut feeling. I guess that I tend to look at things from a lower bound point of view first, and would probably, I mean, I think that would be my guess, but not based on anything besides my intuition. And I'm not sure what my other co-authors think.
Avery here. I say 1 bit.
You said 1 bit. Yeah, that's what I remember discussing that with you.
I mean, it seems to me like for any sort of 2 subgraphs, there's a way to label them so you can sort of send feedback back up to a transmitter. Kind of one of the subgraphs responds and the other one doesn't eventually. So then you can sort of resolve collisions eventually. But there's some sort of, I feel there's always some way of labeling with 1 bit an entire subgraph to sort of send a response back up to any 2 nodes causing a collision. So yeah, that doesn't really make sense, but that's my intuition. Sort of turn off 1 subgraph, keep the other one on.
The next speaker is Yannic Maus, and he's currently working at Technion with Keren. And as far as I've understood, like a big part of his research goes around graph coloring, and I think this is his favorite problem. And I suppose motivated by that, he's also giving a talk here about vertex coloring.
Hello, everyone. I'm very happy that I can speak here at ADGA. It's the one workshop that I look forward to every year. And I'm always amazed by the great talks, and I'm very honored that I can speak here today myself. Yeah, unfortunately for medical reasons, I cannot give this talk live. Instead, I recorded this video in advance, and please bear with me. It might be a bit choppy because I had to stitch it together with several parts. So I want to talk today about distributed vertex coloring, classic meets modern. And yes, I also recorded a longer talk, which I also did in several parts, where you get much more information than in this short talk. So I will keep things a bit short in this talk. So what I want to talk about is classic local models. So you have this communication network, and it's abstracted as a graph, and you have unique IDs, and I will focus on deterministic algorithms in this talk. And then you have communication in discrete synchronous round. Our complexity measure is just the number of rounds. And one thing I want to point out here, that usually you have an ID space, but all the things I will talk about here in this talk, they also work if you're just given an input coloring together with a port numbering. And the problem that I'm mostly interested in here is the vertex coloring problem. So we want to compute the proper coloring of the graph. So every node should output a color such that adjacent nodes get different colors. And usually our goal here is to get delta +1 colors, where delta is the maximum degree of the graph. And this is because centralized, it's super easy to compute such a coloring. We can just iterate through the vertices in an arbitrary order and always pick a free color at a node, because at most delta colors are blocked by your already colored neighbors. So the crux here in the distributed setting is that at the start, when you start the algorithm, each node does not know the communication network, just knows its own ID. But then also at the end, you just need to output your own color. And one thing which is a bit unusual maybe, or an unusual viewpoint, which doesn't get much attention, the start here is actually going to be quite important for this talk. What can you do with your initial knowledge? It doesn't get too much attention usually, but yeah, some problems you can just solve with your initial knowledge. For example, if you have unique IDs, the problem to output a unique ID is trivial. But also if you want to compute the coloring where the number of colors is the same as the size of the ID space, well, you just output your ID. But there's a lot more that you can do. with your initial knowledge, and this will be important. So in the longer talk, I would now zoom out a bit because there are a lot more problems in this area other than the vertex coloring problem. And in the long talk, I give you, I think, maybe not a complete survey, but a pretty detailed survey about the state of the art. Where do we stand for all of these problems? What are the phenomena that we get there? For example, we can also color a graph with delta colors instead of delta +1, and we also know results there. And for edge coloring, we also have interesting observations. So now in this short talk, I will directly zoom in to the vertex coloring problem. So what do we know about this delta +1 vertex coloring? Well, on one side, people have looked at the complexity mainly as a function of n. And here we have, since a breakthrough result from this year, polylog n algorithms, which is considered efficient and was an open problem for a long time. But then people also have looked at the complexity that is mainly expressed as a function of delta, the maximum degree, except for this log star n term. And this is what I want to talk about today. So I want to talk about our result, which is actually also presented here at this year's DIST, which gives an algorithm for the vertex coloring problem, which has a runtime of roughly square root delta, except for this log star n term. And just for the people that know what the congest model is, it's like the local model with smaller messages, I want to say that we can almost meet the state of the art here for the local model in the congest model. The runtimes are a bit worse, but we also have polylog n round algorithms. And we also have, well, not a square root delta algorithm, but also a sublinear in delta algorithm in the congest model. And this was actually the first sublinear in delta algorithm. But before we talk about the state of the art or what else has been done in this regime, let me quickly ask, why would we care about this f of delta plus log star of n anyhow? Well, the reason is if you consider here some very large network and this red node up here, well, then I guess you would want the complexity of your algorithm not really to depend so much on global parameters, but only on local parameters. But if you have an algorithm which has polylog n rounds complexity, you have a really large global dependence. Well, usually we consider this polylog to be efficient, but actually, yeah, it's still a pretty large dependence on the size of the network. And there are examples where we can actually compute the solution without any global dependence. So there are problems, for example, fractional dominating set approximation or vertex cover approximation, where we compute solutions without any dependence on them. So why don't we do the same for the vertex coloring problem? Well, unfortunately, for the vertex coloring problem, and also for many other problems, for example, for MIS, maximal matching, we have this log star and lower bound. And this is why we look at algorithms which have a complexity of f of delta plus log star n. So I like to call these truly local algorithms. But I want to point out here, and I want to put this up for discussion, that this is not really a well-defined term here. I don't know what's the right definition here. Should we just allow everything which fits into this runtime of f of delta plus log star n? What should the constant be in front of this log star n? Because another possibility would be just to consider at the model where you don't have unique IDs, but instead you have an input coloring, because an input coloring can actually be checked locally, but IDs, the uniqueness of IDs, you cannot even check locally. So one can question whether these unique ID assumptions actually make sense in a very large network. And before we continue with this, I just want to point out there are actually problems where we cannot have such a truly local algorithm, but we really have an omega of log n lower bound. So problems are delta coloring, 2 delta minus 2, edge coloring, synchronous orientation, and others. And one thing I want to point out here is that if we have an input coloring, this log star, for example, with delta to the 5 colors, then this log star delta log star n lower bound here goes away. while these omega of log n lower bound remains. So basically this log star of n lower bound here by linear is a lower bound on the size of the initial ID space or the input coloring, while this is a lower bound which depends on the number of vertices here. So what's known for this regime f of delta plus log star rounds? Well, as I said, there's this classic lower bound bilinear, and there's also a very classic upper bound bilinear, and this one will be important for this talk today, where we color the graph with delta squared colors in order of log star n rounds. And then there's a lot of research, and I will be very brief on this in the short talk. We have algorithms for delta plus 1 coloring, which reach from order of delta squared rounds to delta over delta times log delta to linear in delta. And at this time, people started to conjecture, is maybe linear in delta a lower bound? And we also showed a lower bound in a weaker model than the local model of delta to the 1/3. So in this model, you cannot count. So for example, this JACM14 algorithm here doesn't work in this model. But it turned out that actually afterwards we got sublinear in delta algorithms, this delta to the 3/4 and then a roughly square root delta algorithm. And today I will also talk about a roughly square root delta algorithm here. And you can see the improvement in the runtime is marginal. It's only this log star delta. And the main contribution is actually not in this runtime improvement, but rather in the technical insights that we gain here. And while in the long talk, I will actually talk about almost all the algorithms that you've seen here in this regime, and you will get at least a feeling for what all these algorithms look like and are like. Here in the short talk, I will only focus on these two things here and the core ingredients for these two things. And what are the core ingredients for these two things? Yes, so I will focus on this linear algorithm and then what we call linear for lists, which is basically a list coloring version of the above problem. I will later tell you what that means. So what is the core of linear's color reduction? Of linear's algorithm? The core is a color reduction which takes an input coloring and computes a new output coloring with k colors where k should be smaller than the number of input colors. And k is roughly in the order of delta squared. You can ignore all the polylog terms here. So if you iterate this algorithm and you take your IDs as your input coloring at the start, then you basically get linear's result. How does this algorithm work? It's just one round and it's very simple. So first, every node without communication, and I will later tell you how you do this, select a candidate color set, a set of colors that you would like to output. So everyone gets such a candidate color set. Then you learn the candidate colors of your neighbors. And then you just pick a color which in your candidate set, which is not a candidate for any of your neighbors. So what do you need for this to work out? Well, you need that this is non-empty, that you have a candidate color remaining. One way to reach this is via a so-called low intersecting set family. What is a low intersecting set family? Well, you have a family of sets such that each two of these sets have a small intersection. So now if you also require that each set is large enough and you pick these sets as the candidate color sets, so you need one of these sets for each input color, well, then you obtain that you always have a color remaining after removing the candidate colors of your neighbors. Because if you from your set remove all the intersections with your neighbors, you only remove a little bit for each of your neighbor, and your set is large, you have something remaining. So in the long talk, I will give you a greedy construction on how to construct such families. For here, I just want to say that these families exist for a certain choice of parameters. And because of the existence, we can solve the problem of assigning a candidate set to each vertex, such that neighboring candidate sets have a small intersection, and such that each candidate set is large. We can solve this problem in 0 rounds without any communication, because everyone can just hard code their input color to one of these sets in the family. So let's look at this algorithm again. So the problem that we want to solve is this problem P0 of coloring with roughly delta squared colors. And we can solve it in 1 round if we first solve this problem P1 of assigning each vertex a suitable set of candidate colors. And now, because a large family of such candidate sets exist, which are low intersecting, we can solve this without communication by hard coding our input color to a set in this set family, by just using our initial knowledge. So now let's look at the main contribution of our paper, the main technical contribution, and this is a list version of this. So we solve list coloring, which means each vertex V has a list LV of available colors. And so a node has to output a color from its list. And by delta squared, or roughly delta squared, please ignore the polylogs here, coloring, we just mean that each vertex has, each list has to be at least of this size. And now we would like to solve it with the same method in 1 round. We want to first solve this problem P1 prime. We just give each vertex a list of candidate colors, and then you exchange these and you just do the exact same process. What you need now is that this list of candidate colors has to be a subset of your own list, because you need to output the color from your list. And one can show that this problem, regardless of how you construct such a family, cannot be solved in 0 round without communication. So what we do in the paper is we solve it with a very similar approach, but a higher order approach of this. So what we do is we solve first a different problem, P prime 2. And in this problem, each vertex selects several candidate sets of colors. So for each vertex, you have these sets of candidate colors, SV1 to SVR. And then in 1 round of communication, you learn these candidate sets of your neighbors, and you see which ones work together, which ones do not. And then you just pick one which is not in conflict with any of the sets of your neighbors, which will solve this problem P1 prime. And now it turns out that this problem is actually a problem, even so it's a rather technical problem, and it's not super trivial to just write it down, that this is a problem which we can solve with the initial knowledge without communication. So it's a higher order version of this low intersecting sets that we solve here in 0 rounds. So while this algorithm here of 1 round is super trivial, the magic and the difficult part is actually to show that you can assign such a suitable family and hard code it in 0 rounds. So let me put our main technical contribution, lineal for lists, on this slide here. So in 2 rounds, we can solve list coloring if we have this minimum size on each list, so roughly delta squared. You can see we have some dependence on the number of input colors and also on the color space, but I won't detail on this. In the long talk, I will now give you all details on how you can use this result to actually get a delta +1 coloring algorithm with roughly square root delta time. Here, I just want to say it's based on the observation that this lineal for lists also works if you have just a bound on the out degree. And there are methods to partition a graph into several graphs with small out degree. And in the long talk, I will also tell you how you can partition this and give you all the details of this blue arrow here. Here, just to give you some food for the discussion, I just want to quickly conclude with a few things. So are these low intersecting families the right objects to study, but at least they live in the right universe. What do I mean by this? Consider this linear color reduction. We wanted to solve this problem P0 of coloring with roughly delta squared colors. How did we do this? Well, we constructed a sequence, an upper bound sequence of problems until we reached a trivial problem. The sequence was such that we can, in one round of communication, go back from a solution of pi plus 1 to a solution of pi. The trivial problem that we reached here, we just had a short sequence with 2 problems, was the problem of assigning these candidate lists. The very interesting thing here is that there's also a dual concept of a lower bound sequence. Here you define a sequence of problems P0 until Pt, where the last problem is non-trivial. And now what you also meet here in this sequence is that pi plus 1 is at least 1 round easier than pi. If you have such a sequence, then you have a lower bound of t rounds for your original problem P0. And the very nice thing is, and there's a long ADGA talk by Sebastian Brandt on this whole topic here, is that he can construct these lower bound sequence mechanically. And if you do this mechanical construction for the vertex coloring problem or the list coloring problem, you get exactly objects in this universe that we used here to solve the problem. So I think it's at least the right direction to actually learn more about this problem. So let me quickly finish with just a few open problems. So one open problem is clearly lower bounds, because we don't know any small omega of log star n lower bound. And we don't even know whether this log star lower bound holds if we increase delta to be log n. Note that if delta is log n, I won't tell you now, but we can, for example, compute the delta to the 4 coloring very quickly, but if delta is 2, we cannot. And then we have lots of other open problems. I'll just state a few. So what we've seen is this roughly square root delta runtime. And one problem is, of course, there's this annoying square root log delta term here. Can we remove this? I don't know. And I also don't know whether the square root delta is actually a natural barrier. It seems to be with our current techniques, but maybe there are much better techniques. Then what I didn't talk about today is this regime of f of n, where we have polylog n rounds algorithms. But these algorithms are based on a very generic method, so they all rely on a concept called network decomposition, and they're not really tailored for the problem of vertex coloring. So I think one open problem is to come up with more or further simple and meaningful algorithms for coloring and MIS. I think we have a few for coloring. I will talk more about this in the long talk, but none, for example, for the MIS problem. And of course, there's a lot that I didn't cover today and also don't cover in the long talk. So what should we look next? Well, I think we should understand the speed up, not just for lower bounds, but also for upper bounds. I think I didn't mention the term before. Speed up are these lower and upper bound sequences. Then we should also understand list coloring. All the recent achievements have been through list coloring algorithms, but for example, this problem has not been looked at for lower bounds. And we should focus on out degree versus degree. In all these recent algorithms, it's essential that we look at out degree, and the algorithms also work with a bound on the out degree and not just with a bound on the degree. And then we should also look at what can we do in 0 rounds? How does the ID space help us? What can we actually solve here in 0 rounds? And one thing I want to say that also in the long talk, I don't have a detailed comparison with the works of Regnault, Heinrich Kozowski, and also not the one with Barenboim from 1415. Even so, many of our ideas are inspired by these works, but I think comparing our work with these works actually deserves its whole own talk. And I apologize for not having this in the longer version.
So do you know of attempts of dropping the dependency in n completely by introducing some other local parameter, one that rules out linear's lower bound, like in any distance d neighborhood, the max degree is at least b?
Other local parameters have been considered, like aberracity, but not the one that you suggested. But I don't think they really rule out linear lower bound. So I don't know whether there's any parameter we looked at which really rules out linear lower bound. This is why I said it's already open. If delta is large, we don't know whether the lower bound still holds. So even so, it's one of the most classic results in this area. I think we don't know so much about this, and it's always taken for granted. So somehow, but it actually just studies the special case of delta equals 2.
There is the question of how many initial curves there are, right? And if they're less than n, then the lower bound will also be less than. I mean, yes. The lower bound is log star number of initial curves. Maybe that's a parameter that's worth mentioning.
Yes, I think I also saw. I hope I said this in the video as well. Like this log star is actually depends on the initial colors. But
okay, and then there's Sebastian asking, how about girth as such a parameter?
Well, the cycle, if you have cycle on n nodes, the girth is pretty big, right? And this is where the lower bound was proven. So you mean like you get the promise that you have a small girth? Is that the question?
Yes, in some sense. I mean, having it would explain the linear lower bound, for instance, right?
Yes, I think it's very crucial. Also, like I didn't put it on the slides, but I think it was already in your ADGA talk last year about speed up that we understand how to use small cycles, whether we can benefit from these and whether we can benefit from a small girth, because the speed up technique only works if you have a large girth. Like as soon as you go above the girth, this lower bound technique for proving lower bounds only goes up to the girth, as far as I understand. And I think, yes, we should really try to understand what happens with small cycles.
Well, linear, I mean, take a cycle where you connect to distance 2 in your cycle. Now everywhere you have small cycles, but you can still not color it in less than log star in rounds with constant colors.
Yes, I guess that's true. Yeah, you probably need a more robust measure, which also counts how many cycles you have and how
you still essentially have a cycle you have to color.
Yes.
It didn't really change the problem.
Yes, but you need to have a parameter where you cannot fake things like this and just immediately that you're immediately back at the original setting. So I don't think any such parameter has been looked at. I know there's a lower bound of log n if you want to color as a function of the aberracity. I think less than a squared colors of the aberracity, or even any function of the aberracity, I think. Then there's a log n lower bound, because aberracity would be such a parameter which more talks about local density.
And yes, thanks for the talk, Yannic. It was nice to have you around, even if for such a short time. Dennis is a postdoc at the University of Freiburg, working with Fabian Kuhn. And as mentioned already in the previous talk, he was part of this success story of this round elimination technique. And for example, they got the Fox best paper last year using this framework. But also Dennis, if I understood it correctly, personally programmed the round eliminator so that anyone can basically go with their web browser and do lower bounds automatically on the internet, which I think is kind of cool. But besides that, he has also done many other things. And now, as far as I understood, this edge coloring talk doesn't really have anything to do with the round elimination technique. And now I will let Dennis take over.
Okay, thank you for inviting me. It would have been very nice to have see you all here in Freiburg. So I'll talk about the joint work with Alkida Balliu and Fabian Kuhn about distributed edge coloring. But let's start first from the model. So we are in the local model of distributed computing. So we have a network that we can represent as a graph, where nodes are machines and edges are communication links. And this model is synchronous, and we do not restrict the bandwidth nor the local computation. And we are interested in the number of rounds of communication that are required to solve a problem. And in this talk, we will consider symmetry breaking problems. And I will not give a formal definition of what symmetry breaking problems are, but the intuition is that we consider problems where the main requirement for neighboring nodes is to give different outputs. And the challenge here is that there are nodes that have very similar view. If they just gather their view, for example, in their running time, they have very similar view, but they have to give different outputs, so they have to break their symmetry. So this is a very non-formal definition of symmetry breaking. It's just that nodes that are neighbors have just to give different outputs. And there are 4 symmetry breaking problems that have been studied a lot, not only in the local model, but in the whole distributed computing setting, that are maximal matching, maximal independent set, delta +1 vertex coloring, and 2 delta -1 edge coloring. And one common feature of these 4 problems is that all of them are very easy in the centralized setting, meaning that all of them can be solved with a very simple greedy algorithm. And the point is that, okay, they are easy in the centralized setting, so let's see how hard they are in the distributed setting. And we know something about this problem. I mean, they have been studied a lot, so we know quite some stuff. And for example, we know that if we are given an algorithm for maximal independent set, we can easily use it to solve maximal matching by just running it on the line graph. That's something that can be done easily in the local model. And with a different kind of reduction, we can also show that maximal independent set, an algorithm for maximal independent set, can be used to solve delta +1 vertex coloring. And another reduction, easy reduction, shows that delta +1 vertex coloring can be used to solve 2 delta -1 edge coloring. And we know more about this problem. We know since this year, actually, that they can all be solved quite efficiently. They can be solved in time polylogarithmic in n, where n is the size of the graph. But now we want to know more. We want to know how local are these problems, meaning that we want to know what is their complexity if we want to spend the minimum possible as a function of n, that is log star n, because log star n is a lower bound for all these problems. And we are allowed to spend some function of delta also. So Yannic talked a lot about why we are interested in this kind of complexity. So I will not give more details on that. And instead, I will say what we actually know for these 4 problems in this regime of log star n plus f of delta. So let's start from maximal independent set. First of all, we have this log star n lower bound. And we know that we can actually spend just log star n as a function of n if we are allowed to spend a lot as a function of delta, if we are allowed to spend linear in delta. So we can match this lower bound as a function of n, but we have to spend a lot as a function of delta. And since last year, we know that this is actually tight. So this is a bad news, actually, that says that we really have to spend linear in delta unless we spend much more than log star n. We have to spend at least log n over log n. So this is a lower bound that is a really bad news, basically. And for maximal matching, we know exactly the same. We know that we really have to spend linear in delta unless we spend a much larger than log star n dependency as a function of n. Now, for coloring problems, the situation is different. We know that they can be solved in sublinear time. They can be solved in root delta. But unfortunately, we have no lower bounds at all as a function of delta. So we know that we can beat this linear in delta, but we really don't know I mean, this is better, but it's still a lot, root delta. We would like something like log delta maybe. So we would really like to see a lower bound here. And for two delta minus one edge coloring, the situation is even different. We know that this problem, since this year actually, we know that this problem can be solved in sub-polynomial in delta time. We know an algorithm that runs in 2 to the big O of root log delta. And also, of course, also here we don't have any lower bound. So this is the picture. We have that maximal independent set and maximal matching really require linear in delta. We have lower and upper bounds, while for coloring problems, we know that they can be solved faster than linear in delta, but we have no lower bounds. We only have this log star n. And in our work, we studied this 2 delta minus 1 edge coloring problem. And we tried to improve this delta dependency. So let's see more in detail what we know about edge coloring. So first of all, the same algorithms that work for delta plus 1 vertex coloring can be run on the line graph, and they directly give a 2 delta minus 1 edge coloring. So this directly gives a root delta algorithm for edge coloring. And then for edge coloring, we know more. For example, we know that if we allow even more colors and we allow linear in delta instead of just 2 delta minus 1, then this problem can actually be solved faster than root delta, since there is an algorithm that runs in just delta to the epsilon for any constant epsilon. And actually the constant in front of this big O depends on this epsilon. And since this year, we know something better. We know that 2 delta minus 1 edge coloring can be solved in this 2 to the big O of root log delta. So this is our result. We improved this complexity as a function of delta, and we proved that 2 delta minus 1 edge coloring can be solved in 2 to the big O of log squared log delta. That can also be written as log delta to the log log delta. So this is what we do. So this is quasi polylogarithmic. But what we do actually is to solve something harder. We show that the degree plus 1 least edge coloring problem can be solved in time quasi polylogarithmic in delta. So let's see what is this problem. In the least variant of edge coloring, each edge has a list, and we want to, for each edge, pick a color from the list such that all neighbors have a different color. So for example, here there is orange, so this color is valid for this edge. And in the degree plus 1 list edge coloring, we must have that each list must have size at least the degree of the edge plus 1, where the degree of the edge is the total number of neighbors of the edge. For example, this edge has 3 neighbors here, 2 on one side and 1 on the other, and the list has size 4, so 1 plus 3. So this is the problem that we consider, and it should be clear that this is that 2 delta minus 1 edge coloring is just a special case, because if the maximum degree of the nodes is delta, the maximum degree of the edges is 2 delta minus 2. So we are allowing the same list of 2 delta minus 1, so 1 plus the maximum degree for all edges. Now, before giving the intuition and some details about how we solve this problem, I would like to explain why we solve list coloring instead of just coloring. So it's not the case that we just solved edge coloring and then we noticed that we could extend our result for list coloring. But what I want to convince you is that list coloring actually helps if we try to use recursion. So to explain this, I will just take an example of an algorithm that doesn't work, that is based on recursion, but is not based on list coloring. And so let's see this algorithm. It's very simple. We start from a graph of maximum degree delta, and we try to color the edges. It's not a proper coloring. It's just a coloring of the edges, such that the graph induced by each color class has maximum degree delta over 2. If we manage to do this, then we can just independently recurse on each subgraph. And at each step, we halve the degree of the maximum degree. So in log delta steps, we would terminate and use 2 to the log delta colors in total, so delta colors in total. Now, we cannot color all graphs with delta, delta colors for the edges. So something should be wrong here, but before going there, I just have an animation for that. So we want to do this. We color edges red and green, and then we recurse. For example, the red edges we color with blue and orange. So in log delta steps, we just terminate. And the problem here is that this step is actually too hard. We cannot color the edges such that the maximum degree of the graph is just delta over 2. So this would give too few colors in total. So we can prove a lower bound for this. I mean, for the cases where it's solvable, and in some other cases, it's just not solvable at all. But we could try to relax this. We could try to allow C colors. And we want to color the graph such that the maximum degree of each graph induced by edges of the same color is big O of delta over C. Now, the constant in front of this big O here is actually important. If we use a constant that is too small, then this problem is actually too hard. It cannot be done efficiently. While if this constant is too large, then by recursing, at the end, we get too many colors actually. We don't get 2 delta minus 1 colors, but we get more. And it seems not possible to find a constant to put here such that we just get the right amount of colors, and this problem is easy. So what is the problem here? The problem is that if we do not use list coloring, and we want to use a recursive algorithm, we somehow have to early commit on the colors that we are going to use in each subgraph. So we do some defective coloring, and then we have to fix the colors that we are going to use on that subgraph, and we cannot change later. So this is the issue. While if you use lists, we could somehow leave some parts uncolored, color some graph, then update the list of these edges and remove the colors used by the neighbors, and then just recurse on this subgraph. So somehow list coloring is what allows us to use recursion in some nice way. So that's why we consider list coloring. As we will see, our algorithm uses recursion in many different ways. And that's why we use list coloring, basically. So now I will try to give some intuition about how we solve this problem. But first, let's see some definitions. So this is the problem that we want to solve, that is degree plus 1 list edge coloring. And we will also consider some relaxed version of this problem, where the size of the list is at least beta times the degree of the edge plus 1. And we say that this version of the problem has slack 1, while this version of the problem has slack beta. So the idea is that the lists are at least beta times the degree, and this variant is actually easier because edges have more choice for their colors. So this is just an example. Here we have an edge with degree 6. We have 7 allowed colors for this edge, so the slack is 1 because the list is 6 plus 1. And this is slack 2 because the degree of the edge is still 6, but the list has size 13, that is 1 plus 2 times 6. Another definition that we need is this T beta C. And with T beta C, we mean the time required to solve list coloring when the total number of colors in the graph, so the total palette size is C, and the slack is beta. So intuitively, if we increase beta, we get an easier problem because we allow more colors on each edge. And if we decrease the total palette size, we also get an easier problem because if the total palette size is small, it also means the degree of the graph is small. And this is the very high level idea of what we do. So the first thing that we do is to show how to solve a hard instance where the slack is 1 by just solving many easier instances with slack beta. So we show how to decompose this harder case in many easier cases. And so now we just have to focus on solve this easier case, and we just spend an overhead of beta squared times log delta. Now this was actually known, so our main contribution is in this second step. And in this second step, we show how to solve actually this easier instance. And the high level idea is that we split the total color space in p parts, and we find a way to efficiently assign subspaces to the edges, and that's where we spend this log p times t1p, such that then we can efficiently recurse on each graph induced by edges that shows the color subspace. So we gain in the palette size because it's smaller, but we lose in the slack. But if we start with a large enough slack, then this is fine. And then if we choose the right parameters and we solve all the recursions, this is what we get. We get an algorithm that runs in log delta to the big O of log delta that can be also expressed as 2 to the log squared log delta. Now, this was already known. I'm not going to give details about this. There are details in the full version of the talk, but now I will just give some intuition about this. I will actually show some pictures to better explain this problem. So here we have a graph where the slack is large. So it means that every edge has a list of colors, available colors, such that the size of the list is quite larger compared to the degree of the edge. And this holds for every edge. What we want to do is to split the color space like this. And then we want to assign a subspace to each edge like this. And now the new colors available to each edge is the intersection between the old available colors and the subspace that the edge chose. And we want to do it in such a way that, so here the new lists get smaller, but also the degree gets smaller. And we want that the ratio between the size of the new list, so the sublists, compared to the new degree given by edges that shows the same subspace is still large. So we don't want to lose too much in this slack. So for example, here, this list is still size 4, and the degree of this edge is 2. So at least here, the size of this list is still large enough to make the problem solvable. So this is what we want to do. Now, the first step here to split the subspace is actually very easy. We just split it in some way. We don't have to communicate to do that. And then this assignment is what takes this log p times t1p. And if we do this, then we have edges that have like independent subspaces, and we can just recurse independently on each subgraph. So this is where we spend this other t beta over polylog p c over p. Now, in the full version of the talk, I will talk about how we do this. And here I just give the intuition. And the idea is that we convert this subspace assignment to a new list edge coloring instance. And the idea here is that we have p colors where each of these colors correspond to one possible subspace. And we have lists because edges are only allowed to use subspaces such that their intersection with their own list is still large enough. So this is the trick that we use. And actually we need to convert this subspace assignment to log p list coloring instances. And that's why we have this log p times t1p. So now I will just give a summary of the algorithm. So the first step is to convert a hard list coloring instance into many list coloring instances that are easier, that have larger slack. And actually also here we use some kind of recursion that I didn't mention. And the second step is to show how to solve these easier list coloring instances. And we do this by trying to split the color space and converting this assignment of subspaces into a new least coloring instances. And also here we have to recurse quite a lot. So now I will conclude with some open questions. First of all, our algorithm does not seem to work directly in the congest model, where the messages should be small. And the idea is that each time we apply recursion, we have to update the lists of the edges. And now the issue is that the lists of the edges are saved on the endpoints of the edges, so on the nodes, because the nodes run the algorithm and not the edge. And it seems that updating these lists such that the endpoints agree on what are the colors available on each edge require a lot of bandwidth. It could require linear in delta, basically. Everything else is actually efficient in the messages. It's just this part that we don't know how to improve. So it would be nice to make this algorithm work in the congest model. The second open question is about upper bounds. So we showed that 2 delta minus 1 edge coloring can be solved in time quasi-polylogarithmic. And this doesn't really seem to be the right answer. I mean, it's just not a natural complexity somehow. So it would be nice to show some polylog delta algorithm for edge coloring. And then a more important open question is about vertex coloring, where we have still some polynomial in delta upper bound. And one of the reasons for this seems to be the following. For edge coloring, we know how to do a big O of delta over C defective C coloring, while for vertex coloring, we only know how to do a delta over C defective C squared coloring. So it would be nice to see if we can do this delta over C defective C coloring also for vertex coloring. This could imply something for some better complexity for vertex coloring. Last open question is about lower bounds. So in the last 2 years, basically, we saw lower bounds for MIS, maximal matchings, and ruling sets. And all these lower bounds are based on this round elimination or speed up technique. And it would be nice to find a way to apply this technique also for coloring problems. It seems that we are still quite far from that, but it would really be nice to find a lower bound as a function of delta for coloring problems. So thank you.
So Dennis, can you say something about the color space dependency and the final result, or does your algorithm work for any color space?
So the question is, if we allow somehow more colors, if we can do better? Is that a question? Like we allow a larger color space at the end, or larger?
No, the question is if the lists come from a really, really large universe, how does this influence the runtime?
The lists?
Because this was actually somewhat crucial.
Oh, you mean if the lists are small, but the color space is large, right?
Like it's like, yeah, maybe even much larger than N, or like just from some really, really large universe.
I don't know. I mean, I think I think this upper bound would be bad in that case, because I mean the running time that we get really is really obtained by reducing the space, like it divides the space multiple times. So I don't really know what would happen in that case.
I think you basically have to replace delta by the size of the space.
Yeah, exactly.
Yes, but you get some delta and some color space dependence, yes? But
no, all the deltas you have to replace, I think, because it's just the sweet spot in the recursion. You would just basically reduce color space of size C to root C, and you need log C recursion levels.
Yeah.
I guess you could get log C to the other log C.
Okay, thanks.
So I want to ask the obvious question of like, what do you think? Are you close in getting to the, like you had this to the log squared delta thing there? And I mean, I know that you posed as a nice open question, if you can make it faster, but what do you think? Like, do you need to invent something totally different to get there, or did you get close to it?
I don't really know. I mean, I think the right answer should be polylog delta, but I mean, we tried to improve the parameters for the recursion, but we couldn't get something better than this quasi-polylogarithmic. I don't know if we really need a new technique or just something slightly better. I mean, it could be both, like both things could work. I just don't know.
Okay, so it does make sense for Yannic to read through your proofs and figure out how to improve it.
I mean, you should have already done that, right?
Yannic asked, are there any reasons that not everything can be done in O of log star n rounds, I guess, without any delta dependency?
It could be an option, right? I mean, we know that delta squared can be done in just log star. So it could be an option that coloring can just, delta plus one coloring could be done in log star, right? I mean, we still don't know. I mean, it could be, but I mean, we are
that
really
would be
far
awesome.
From that, right? We are just far from that.
Yeah, that would be awesome.
Yeah, that would be awesome, right?
Then my favorite problem, which is actually nicely here on the slide, is delta over C defective C coloring.
Yeah.
So do you think you got anywhere closer to getting the C squared down to anything sub C squared, or is it still equally depressing?
The point is that for edge coloring, it's trivial to do this. And for vertex coloring, it's, I mean, I really have no idea of what would an algorithm, I mean, what an algorithm that does that looks like. So that's I mean, it could be that it's just not possible. I just don't know. I mean, but the point is that we really cannot use the ideas that we have from edge coloring to do this fast for vertex coloring. It just looks different.
Okay, well, I'm somewhat
happy when we worked on it.
Yeah. No, okay. I'm somewhat happy to hear that, because I'm still hoping that I wake up one day and figure out something new to that.
It would be really nice. Yes.
What does fast mean here? Because with de-randomization we can solve it, right? If we spend.
My version of fast would be polynomial in the number of colors.
Yes. Yeah, this would be fast. I agree.
I think if you get C to the 2 minus epsilon polynomial in the number of colors, there is a good chance we can beat the square root delta for delta plus 1 vertex coloring.
Which is probably the reason why it's not so easy to come up with that. All right, so the next speaker is Michael, and I'm not exactly sure how to pronounce the last name. I guess Dinitz. Sorry if I did it wrong. And he's a professor at the Johns Hopkins University, and he has quite some history in algorithms in general, but I guess that like a big part of it is on graph spanners. And today, I guess we will get a look into some part of that research. And I let you do the rest of the graph spanners talk. Go ahead.
Great. Yeah, so thanks for the introduction, and thanks for inviting me. Just like I think someone earlier said, maybe Yannic, this is always a fun workshop to go to whenever you're at DISC. I always enjoy ADGA. So yeah, this is, okay, let's just get started. So this talk is about spanners, right? As Yara said, I work on a lot of different things, but spanners is certainly one of my favorite things to work on. So many of you probably know this definition, but in case you don't, if I'm given a graph, a subgraph is a t-spanner if distances are stretched by at most t. Right? And because it's a subgraph, actually, they're also at least what they were originally. So basically, all distances are preserved up to t. In this, I should say, not this paper, in this talk, this graph is kind of undirected and connected, but you can, of course, talk about more complicated settings. And another kind of nice warm-up to see is that because this notion of stretch is multiplicative, all I need to do is preserve the edges, right? If I preserve the edges, I preserve all pairs, which is not true for more complicated notions like additive stretch, which are super interesting, and there's many papers about recently in this community and in others, but I'm not going to talk about. Okay, so what I want to kind of talk about today really is kind of this fact that graph spanners kind of really grew out of this community, right? Grew out of distributed computing. So you can see these 3 papers by David Peleg and various co-authors, which kind of are cool because they, they go from PodC to Stock to the Journal of Graph Theory, right? Like you're seeing distributed computing, kind of algorithms in general, or theory of computing in general, and then kind of pure math. And so because of that, like these objects have been of interest to kind of lots and lots of different people and lots of different communities, but really like fundamentally, we keep coming back to them in the PodC, DISC, ADGA communities. And so I'm going to kind of talk today about some recent progress we've made in centralized settings that I think is like really cool. And if you'd asked me, 4 years ago, would we have been able to make this progress? I would have said no, but we have, which is awesome. But for problems that actually make the most sense in distributed settings. Right? So like these are problems that should be looked at in distributed settings. And yet the kind of all the progress we've been making has been only in centralized settings. And the reason for that has been the same. It's that we're really using this thing called the greedy spanner. We're fundamentally depending on the greedy algorithm. So the greedy algorithm, has some very nice properties that I'm going to talk about in a minute. But, as you all know, for whatever your favorite notion of distributed is, right? Whether you're local, congest, PRAMs, MPC, congested clique, whatever, greedy algorithms are tough, right? And like sometimes you can do that, but often greedy algorithms are just seen inherently sequential. And this is kind of one of those examples where, we only know how to do this with the greedy algorithm, and it would be awesome if we could figure out how to do this distributed. And so this is kind of, I thought it would be nice to end the conference or end this workshop on something maybe somewhat technical, but maybe a little less technical than the last few talks, and more about kind of open questions. So if there's, postdocs, students, people who have time listening to this talk, here's some like open questions that seem like hard, but maybe not that hard, but make a ton of sense. And so this is supposed to kind of motivate all of you to go out and solve these problems because you actually know distributed graph algorithms much better than I do, right? Like I occasionally write papers on distributed graph algorithms, but it's kind of not my bread and butter the way it is for some of you. And so hopefully someone will just be able to come up right after in the comments and tell me how to do this. And then I'd be like super excited. That would be awesome. Okay, so I'm going to try to go through quickly. These are the 3 parts from the long talk, but I'm also going to kind of do short versions of them in this talk. Where I'm going to start out with just talking about the greedy algorithm and what it is. Then talk about these 2 different settings. So one, what we call LP norm spanners, or the LP norm objective, and another on fault tolerant spanners. And of course, like once I throw the words fault tolerance in there, it's kind of obvious what the connection is to distributed computing and distributed algorithms. But we'll see that even for LP norms, the setting where it makes the most sense is somehow distributed. Okay, so let's talk about the greedy algorithm. Okay, so I call this is not the first result on spanners, right? But I showed you those 3 papers of David Peleg. But this is what I tend to call like theorem 0 of spanners. This is the basic theorem. Everything else is built off of one way or the other. This says that every graphs allows spanners of stretch 2k minus 1 with n to the 1 plus 1 over k edges. And if you believe this thing called the Erdős-Wirth conjecture, which many people, but not everyone, certainly not all my co-authors, for example, believe, but if you believe it, then that bound is tight. Okay, so this is kind of great from the early 90s, says modulo this conjecture of Erdős, like we totally understand what's possible with spanners. And one thing to note about this is that the statement of the theorem, like as I phrased it, and as is in kind of the original papers of Althofer, is existential, right? This just says that these graphs exist, these subgraphs exist. But it turns out like this is actually algorithmic. So the Althofer paper gives this very simple greedy algorithm that does this. Okay, so here's this greedy algorithm. It's kind of the obvious algorithm. It's the obvious generalization of Kruskal's MST algorithm, for example. It basically says, go through the edges in non-decreasing weight order. And if I need to add an edge, then add it. And if I don't need to add an edge, then don't. Okay, so it's the obvious greedy algorithm. So you kind of see I have some animation-ish that says, okay, I'm gonna like keep adding these edges. Now I consider an edge and I don't need to add that, right? This V2, V3 distance is already preserved up to a factor of 3. So I don't add it. That V2, V3 edge is already preserved up to a factor of like 2 in this case, but even less than 3, so I don't need to add that. So this would be my spanner that I get at the end of it. And one important property of the greedy spanner is that the girth is large, so at least 2k plus 1. So you can kind of see it's just never going to complete a small cycle because that last edge that it's considering adding, it just would say, hey, I don't need to add this. I've already got good enough stretch. Right, so this greedy spanner has the property that it has large girth, and that's kind of what we're going to utilize over and over and over again. The downside of this is it seems hard to make this distributed. Right? I don't know any way of making this algorithm distributed in any kind of non-trivial way, and that's kind of the problem. Okay, so let's talk about LP norm spanners. So this is 2 papers, one from iCalc, one from Approx, with the same authors and with deceptively similar names, deceptively similar titles. I'm really not going to talk about the second paper at all. So this is some approximation algorithms, which is an area that I love, but is a little bit outside the scope of this talk. So we're just going to talk about this first paper. Okay, so I want a 2k minus 1 spanner, like fine. What else do I want? And you can kind of see from that theorem 0 that the kind of classical thing to want is minimizing number of edges. Right? I want few edges. Okay, so I'm trying to sparsify, right? That's intuitively the whole point of spanners, is that I'm giving a sparsifier that preserves distances. There is this issue, right, which is kind of obvious in distributed settings, right, which is that, I often want to use spanners as an overlay network or as something on my distributed, in a distributed setting. And then, of course, like I care about the degrees, right? Like a star is not the same thing as a path, right? A star is not the same thing as an expander. Having high degree nodes causes load, causes, all sorts of bad things to happen in distributed settings. Right? If these are physical switches, of course, then, I physically don't have that high of a degree. Okay, so that's a problem, right? And of course, like I want small edges, but I also want small kind of degrees. Right? So maybe I want instead to minimize the max degree. That's great in distributed settings, minimizes load. Has some real cons, has some real problems, right? The most obvious of which is that, for example, if I give you a star, like all you can do is give me back the star, right? There's no kind of spanner of the star other than itself. So you can't kind of give those same trade-off theorems. But what I want to focus on is actually the slightly more subtle issue it has, which is that, suppose way over here in this part of the graph, there's something that causes me to have large degree. Okay, like that can happen. Somehow, if what I care about is minimizing the max degree, that gives me license now to do whatever the hell I want in this other part of the graph, where maybe I could have much smaller degree. Right? Like, there's no reason, like, why is the fact that over here I need large degree, does that give me a license to use like crazy degrees somewhere else in the graph? Right? Like, that seems bad. So we want something else. We want something that encourages the max degree to be small, but also encourages all other nodes to have small degree, even if for some reason the max is forced to be large. And of course, this is probably not going to be a surprise to many of you, because this is certainly not really a new observation. But if I consider the vector of degrees in a graph, right, then the number of edges is basically the L1 norm, right? It's half the L1 norm. And the maximum degree is the L infinity norm. Right? These are just by definition. And of course, now this suggests the obvious interpolation between the two, right? Which is to use the LP norm. Right? So I say the LP norm objective is to find a spanner that minimizes the LP norm of the degree vector. So in other words, the sum of all the degrees to the P, all to the 1 over P. Right? So, this is not some crazy thing, right? Like the L2 norm, for example, but the LP norm more generally, is a totally standard objective with like thousands and thousands and thousands of papers in the clustering and scheduling literature, for example, right? Like people talk about k-means all the time, right? That's L2 norm for clustering. People talk about L2 norm in scheduling like all the time. This idea that the L2 norm is somehow giving performance that makes more sense than either just the L1 norm or just the L infinity norm is a kind of classical observation, which for some reason hasn't really made its way into network design generally, or spanners in particular. I don't exactly know why, but okay, we're going to do that. Okay, so we introduced this objective in this iCalc paper, and we kind of proved this theorem, which is the equivalent to theorem 0. Right? So this is, assuming the Erdős-Girth conjecture, the right trade-off here. It says that for every k, just like before, but now also for every p, you can build a 2k minus 1 spanner with LP norm, which looks like this. It's either n to the k plus p over kp, or it's n, whichever is bigger. One cool thing about this, but also one crappy thing about this, is that it's the greedy spanner, right? So like we know how to do this centralized because it's the greedy algorithm. No idea how to do this distributed. Right? But a cool consequence of that is that the greedy spanner doesn't take p into account at all. So you're kind of simultaneously doing this for all p, which is a neat property to have. And just because that n to the k plus p over kp is hard to visualize, like here's kind of what that looks like, right? When I kind of have stretch 3 or stretch 5 or stretch 7, you can kind of see what this trade-off looks like. And it's actually maybe even more interesting. Yeah, okay. In the long talk, I kind of say about how we kind of prove this and what the techniques are, because it turns out you only kind of really need to prove the bounds for like these points sitting here, and then the rest is implied by standard inequalities. But I'm not going to go into that now. Okay, so how do we prove this? Right? Like I said, we just prove that any graph of high girth has this LP bound. Right? So then that immediately implies the greedy spanner has this LP bound. But of course, now how do I do that in distributed context? Like, I don't know. Either like if I want to use the same style of analysis, like which is hard, right? I mean, I'm going to say like this was an iCalc paper in part because Thomas Robinson, the postdoc on this process, did crazy amounts of technical work to get this analysis to go through. It is quite difficult. We need some distributed spanner that has large girth if we want to use that same analysis. And of course, in many distributed contexts, even computing the girth is hard. Right? Even approximating the girth is hard in some of them. So I don't know distributed spanners that have large girth. Or maybe you need some brand new analysis that allows for low girth, right? Because we have distributed spanner algorithms that have low girth. But then I have no idea how to analyze what their LP norm is. So again, very clean open question. For example, take the Boswanus-N spanner, take the Thorpe-Swift spanner, take whatever your favorite spanner construction is, figure out what its LP norm is. I have no idea how to do that, but it would be cool. Okay. Let me now switch gears to fault-tolerant spanners in the last 5 to 6 minutes. So this is a slightly longer series of papers. In fact, these are just the ones that I'm involved with. There's even more that I'll talk about later. That go back to kind of 2009. I first kind of got involved in 2011. And you can kind of see there's some recurring themes. There's something like simple, right? We like being simple. We like being optimal. So, okay. Good. So fault tolerance. So now I'm going back to caring about number of edges. But I want to have some notion of fault tolerance, right? And the motivation here is obvious. It's the same motivation we always have for fault tolerant network structures. Right? If I give you some graph that looks like this kind of graph that's in gray combined with red, right? So like maybe 2 cliques with 2 edges between them. Very easy to build a 3-spanner of them, right? 2 stars connect 2 stars and then connect them, right, with that. But now, of course, like if this node fails, I'm kind of super unhappy, right? I've disconnected this spanner. And not only am I super unhappy because I'm disconnected, I'm super unhappy because I'm disconnected and I made like the wrong choice, right? Like if I had just chosen to use that edge, I would be totally happy, right? Nothing wrong with that then. Right? Like the underlying graph is still totally fine. I'm just now a crappy spanner of that, even though I could have built a good spanner of that. So I want to avoid that. Right? So this definition is due to Chechik, Langberg, Peleg, and Rodity from 2009, and I'll talk about their result in a minute. And it's kind of the obvious definition, but it has some subtleties. So it says that a graph is an F vertex fault tolerant 2K minus 1 spanner if for any set of F vertices I kill, what remains in my spanner is still a spanner of what remains in my graph. Right? So H minus F is still a 2K minus 1 spanner of G minus F. And I'll note that there are some subtleties here, right? This is worth pointing out because it's kind of weird that if G is intuitively not fault tolerant, right? Maybe G is like a tree, then H is kind of N fault tolerant. It's like maximally fault tolerant, right? Because all that I need to be a fault tolerant of what remains of the graph. So if the graph has really crappy connectivity, then I'm allowed to have really crappy connectivity. So you have to be a little careful what you mean here by fault tolerance, but this is kind of the obvious thing, right? Like I can't build a fault tolerant structure of something that is not fault tolerant. So this is comparing to the underlying connectivity in some sense. And the main question here is, okay, like I need n to the 1 plus 1 over k edges just to be a spanner. Like we know that from the girth conjecture, and we can match that in general. How much extra do I need to pay for fault tolerance, right? What's the extra cost? So in 2018, we proved a lower bound here that said you need to pay at least f to the 1 minus 1 over k extra. The question is, okay, like how much more do you need? So here's the kind of table of results. You can see, right, so Cheshik-Langberg polygonality. This is the journal version of 2010. The conference paper was in 2009. And they kind of showed that you can do kind of exponential in f, right? So, okay, like if f and k are independent of n, that's great. With Roby-Krothkammer, we kind of showed how to get f polynomial in f, and also kind of polynomial runtime, right? So if we think of f as being possibly a polynomial in n. In 2018, we kind of got this f to the 1 minus 1 over k, right? So I said that's a lower bound. It's also an upper bound, but we had this exponential in k badness, which then was gotten rid of in 2019 in a PODC 2019 paper by Bodwin and Patel. And then recently, so in PODC 2020, and then in SODA 21, we're trying to get the running time back down to polynomial while still having this optimal size, right? So that's what we finally achieved in this SODA 21 paper, where we have kind of totally optimal size, polynomial runtime. Great. Very happy with this. The downside of these last 4 results, not so much the first 2, especially not the second, but downside of the last 4 results is that yes, they have optimal size for some kind of ish notion of optimal, but they all use the greedy algorithm, right? Or some variant of it. So again, no idea how to distribute this. So actually this 2011 paper, this one with Roby-Krothkammer, you can make distributed, and we kind of show how to do that in the paper, very easy. That can be distributed, but is not optimal size. And we don't know how to get these optimal size spanners in any way other than the greedy algorithm, or some variant of the greedy algorithm, which is what the check star means. Okay, so the greedy algorithm, let me just do it in kind of 30 seconds, is again like the obvious thing, right? Go through the edges, check if I need to add an edge. If I need to add it, then add it. Okay, now of course the check, do I need to add an edge, is there a set of faults that forces me to add this edge? Okay, so here I do that on this graph. And actually now you can see I do have to add that V2, V4 edge, because if V1 fails, I'm going to be in trouble. Right, so I have to add that edge, but then I don't need to add that center edge, so I'm happy. Okay, so great. So Bodwin and Patel proved that this algorithm has optimal size. Very happy with that. Unfortunately, checking that if condition, like is there a set of faults that forces me to add the edge, turns out to be an NP-hard problem. This is what's called the length-bounded cut problem. So that's not great, even centralized. So instead, what we're going to do is kind of relax that. We're going to say we're the greedy algorithm, but ish. Like sometimes we're going to add extra edges that the greedy algorithm wouldn't need to add. And we're just kind of hope that we don't add too many. So in PODC 2020 with Caleb Robel, who I should mention is an undergrad and is applying to grad schools this year. So if any of you are looking for new PhD students, he's awesome. So we gave this approximation algorithm for length-bounded cut, and that kind of immediately translated into an extra loss of k in the size of the spanner. And then in our recent paper, we kind of bypassed this length-bounded cut thing altogether and used some random sampling ideas that I'm not going to go into to kind of give this optimal size in still poly time. And I'll just point out that even with these random sampling ideas, it's still the greedy algorithm, right? It's still running the greedy algorithm on some subgraph. So, okay. Right, so we know how to get polytime algorithms. but no idea how to make them distributed. Maybe, we have these relaxed notions of greedy. Maybe you can come up with some super relaxed version of greedy that you can make distributed. That would be cool. Again, no idea how to do that. Would be awesome. Maybe you can adapt known distributed algorithms to be fault tolerant, right? So like that 2011 paper with Roby works by kind of black box reducing to your favorite distributed graph spanner algorithm that's not fault tolerant, but it's not optimal size. But maybe if I look under the hood of your favorite distributed spanner algorithm, there is some way of making it fault tolerant. I don't know how to do that, but I don't see why it's not possible. So maybe you can do that. That would be awesome. Okay, so in conclusion, I give you these kind of two different spanner settings that we've made, I think, very cool progress in the last couple of years. Both of these settings make the most sense in distributed context, right? Because I care about the load. That's why I care about degrees. Or I care about fault tolerance. It's a very natural distributed or networking thing to care about. But we don't have good distributed algorithms. So we don't have optimal distributed algorithms, I should say. And so hopefully, someone here who's much smarter than me will be able to figure out how to turn these things into distributed algorithms. And that would be super cool. Okay, thanks.
Okay, so Slobodan is asking, would it make sense to, I guess, to use randomized Botswana-Zen more than it's now? Okay, run several copies of it in parallel and overlay the spanners in order to improve fault tolerance. I hope you understand this question better than me if I don't know the background, I guess.
Yeah, so it's a good question, right? So there's this intuition that I talk about in my long talk that I didn't have time to talk about here, which says like, look, if I want F fault tolerance, the natural thing to do is overlay F copies of something, right? Like that is an obvious thing to do. If you had asked me in 2015, is that the right thing to do? I would have said yes. But then we got this F to the 1 minus 1 over K, which says that you don't need to overlay F copies. You can get away with kind of doing less than that. So yeah, and in fact, right, my 2011 paper with Roby does kind of exactly this. It overlays a bunch of copies of Botswana-Sen or of the Durable Gavois et al. Paper. Like it just black box reduces to overlaying multiple copies of your favorite distributed spanner algorithm. So yeah, you can overlay F squared of them using that construction, or no, F cubed of them using that construction with Roby. But if you want to overlay like F to the 1 minus 1 over K of them, or if you want the truly optimal size, I don't know how to do it. Might be able to be done. Would be very cool. You can't do it in a black box way, but maybe you can look inside Botswana-Sen or look inside your favorite distributed spanner algorithm and figure out how to make it fault tolerant. Would be cool. And I should say actually the original, the Chechik-Langberg-Paligan-Radity, overlaid not just F, but like a huge number of copies of Thorpe-Zwick spanner, but showed that somehow because of how Thorpe-Zwick works, when you overlay them, they actually don't add all that many edges. But still it's exponential in F, which is not ideal.
Janne was asking, is there a Metroid formulation of the spanner problem? Because these things you said made him think of Metroids.
Yeah, super interesting idea and question. One of my totally separate lines of work is on Matroid secretary problems and Matroid optimization. So I would be psyched if we could figure out a Matroid interpretation of this. I don't know one. In part, you can see I alluded to this when I talked about the second paper on LP norm. These questions, as I phrase them, are about existential bounds, right? It says, I want something that holds for all spanners. Whereas when you talk about something like Kruskal or MST, right, you're talking about, can I compute the best thing for this input? So that gives, the question of approximation algorithms or optimization algorithms for spanners, which is actually most of my papers on spanners and is something I'm super interested in, but it's super hard. Like all of those optimization questions on spanners are label cover, hard to approximate. They're very weak approximations. And so I don't think there's a Matroid interpretation, but it would be cool if there was.
Okay, and I guess one thing that was before Fabian was Yannic's questions. So which approximation factor would be tolerable when making things distributed?
Yeah, so tolerable is, whatever is interesting, right? Tolerable is not a formal thing. I will say, how should you think of these different parameters, right? How should you think of K versus F versus N, right? Like K is never really more than log N, right? So, okay, I don't love losing factors that are big in K, but aren't a huge deal. So for example, Buzwana-Sen has size like K times n to the 1 plus 1 over K. Okay, like not ideal, but not a huge deal. Whereas F, like I want to be fault tolerant for like large values of F, right? I want to handle polynomial in F number of faults if I can. Right? There's a very interesting talk yesterday by Muraf Parter at DISC on kind of like dual faults or like single faults for other objects for distance preservers, which is like super interesting. But in this context, I'm much more interested in, and I think because we are able to get stronger bounds, we're more interested in like what happens when F gets large, right? So, if you can prove something that has size, this optimal behavior in F, like F to the 1 minus 1 over K, but some horrible behavior in K, not ideal, but would be fine. But what you really want is this kind of, as a function of F and N, really being optimal in size.
Okay, and Yannic's second question was if there are special graph classes that would be exciting.
Again, like interesting is, whatever you're interested in. So yeah, totally, sure. You could think about like spanners are studied all over the place. That's one of the cool things about spanners. So yeah, like in geometric graphs, in bounded doubling dimension graphs, in minor free graphs, in whatever your favorite graph class is. I will say in the more limited you make your graph class, of course, the stronger the upper bounds are, right? So you have to ask for a whole lot more, right? Like there's a lot known about degrees in geometric graphs, for example. And now you have to figure out how all that literature interplays with it, which I haven't done. I know much more about the general graph context, but these problems make total sense there. And, I think would be interesting to look at. And actually, I should say fault tolerant spanners really grew out of the geometric context because geometric land has this nice property that when stuff fails, it doesn't affect the other distances, right? Like if I just have points in two-dimensional space, one point goes away, the other points still have the distances they used to have, right? Whereas in graphs, that is blatantly not true, right? And that's why fault tolerance in graphs is a much harder thing to get.
Yes, so there's no graph class that where the results on spanners excite you a lot.
I mean, that's just me, right? Like I like general graphs, but there's tons of people who've done awesome work in these special graph classes, and I think it's I like going to those talks. I like learning what Shai Solomon and Arnold Filter and Michael Elkin and all these people have been doing. It's just not what I've been working on, but like it's awesome. So I strongly encourage you to go out and do this stuff in those classes too.
So I was wondering for the questions you talked about. Do we know what happens when we go to additive or near additive spanners?
Yeah, great question. More or less, the answer is no. We don't know anything, in part because we know everything through the greedy algorithm. And, additive spanners, the construction is different, right? So yeah, we basically don't know anything. You can get some very weak bounds, right? So I mentioned that this paper with Roby from 2011 is the only thing that's kind of really distributed for fault tolerance. And that strongly depends on being able to, it being sufficient on only being able to preserve edges. Right? So as soon as you go to additive stretch, I can't just look at edges anymore, right? Like I have to look at all pairs. And now I have no idea how to deal with that. If you, for example, had a promise that the diameter was small, or you had a promise that, if you had more promises about what your graphs look like, then you can kind of adapt those techniques. But yeah, we know nothing about these in non-multiplicative stretch settings. And again, they make total sense, should be looked at. It feels hard, right? So in fact, if you allow zero stretch, if you need it to be a distance preserver, that's what Muraf talked about yesterday. And, yeah, like her whole paper was somehow handling two faults, right? Like it's just so much harder to handle one fault or two faults when you have these much stronger stretch requirements. So getting all the way up to like F faults for F large seems well outside of what we can do.
And also the LPs that you don't know anything. The
What
LP
was
norm
that question?
Also the LP norm question, but fault about faults.
Also for the LP norm with additive stretch or with some near additive stretch, I don't know anything. Makes total sense. It's a great question. I mean, the LP norm is particularly interesting too, because somehow, I got into it through spanners because someone asked me this question about max degree, and I was studying max degree, and that's fine. But then you quickly realize, like, it hasn't even been studied in normal network design, right? Like, what about spanning trees with the LP norm, right? What about Steiner tree? What about Steiner forest? So actually, I have a manuscript we're writing up now with Guy Kortzarts and with Shi Li, where we give some of those, approximation algorithms for some of those network design problems with the LP norm. But there's a huge number of open questions all over the place because, we just hasn't been studied.
One more question from Alexandre, which is how about constructing spanners, fault-tolerant spanners against random failures with high probability?
Yeah, again, makes sense, is a cool question. Random failures are fundamentally different than adversarial failures, right? The techniques are kind of extremely different. I don't know any results off the top of my head on random faults. Seems like a cool question. But yeah, I don't know. I think maybe the first question there, which would be super interesting, is can you get bands that are stronger for random faults, right? Do you need to pay that f to the 1 minus 1 over k, right? Like our lower bound says you need to pay that f to 1 minus k for adversarial faults because, like, hey, if I give you this fault set, something bad happens, and I do that kind of for every edge. But if the faults are random, then that lower bound certainly doesn't apply. So it's totally plausible you could kind of get, pretty good fault tolerance almost for free if you're willing to assume random faults.
I actually wondered about this, like if you want to have with high probability for any constant, like how much can you then like essentially design deterministically which failures you need to be able to tolerate? Because I mean, if the probability
for constants is probably not a huge deal, right? Because again, I can just use this layering idea, right? I throw in a bunch of different, I do some subsampling, I throw in a bunch of different, a couple of different graphs here, and like that's fine. It's like constant faults shouldn't be a big deal. The question is if I allow you like something like, log n or root n faults, but they're random instead of adversarial, does that all of a sudden let you start, can you still get into the 1 plus 1 over k or something similar?
Yeah, I was just wondering out aloud, like what is the easiest thing to say?
Yeah, no, I mean, everyone has this goes back also to what people were asking me about the specific graph classes, right? Like everything is interesting. It's just a question of, what I'm particularly good at thinking about and interested in thinking about. Like I've never had any success thinking about random faults because I have no intuition for this. But there's people who have great intuition about random faults, and then it's super interesting. So yeah, totally. Go forth and study it. Like that's kind of the point of this talk is like, there's a huge number of open questions here that I don't know how to solve. And I'm, and I think probably a lot of people here in the audience do know how to solve. So that's cool.
Okay, actually one question that I had that you probably answered was like, you said that we don't have a clue of how to construct the greedy spanners. And does that mean that you essentially need to go through like every edge in the graph and decide whether you take it into the spanner, like linear time algorithm in the distributed setting?
Yeah, I mean, so basically, if you want the honest to God greedy algorithm, which we kind of need for a lot of these results, yeah, like don't know how to do anything. Some of it you can get away, like if I use these these network decompositions, right? Like it's already been referenced a few times, but like if I'm willing to use these network decompositions, I can lose some logs, and then certain things will still work out, but they'll still mostly only work out in the local model. So in congest, so in fact, you can take the greedy algorithm for like fault tolerant spanners, for example, not so much for LP, but for fault tolerant spanners, I can just like do my network decomposition, run the greedy out, take each part of my partition, throw it inside, give it all to one node, have it run the greedy and tell everyone what happens. And like that more or less works. But it definitely depends on large messages. And so doing that in congest or doing that in something else, I don't know.
Yeah, no, the question was again more in this, like, what does it mean not to know anything? Because like sometimes not knowing anything means log n, and sometimes not knowing anything means square root of n, and sometimes it means diameter. And
totally, yeah. So you know, it's right. When I say we don't know anything, what I kind of mean is that if I shoot for actually optimal size for any of these, or actually optimal LP norm, like I don't want to kind of give up on that optimality. What I want to do is now minimize the time. Then I think nothing is known, like other than like n, right? Like totally trivial bounds.
Thanks a lot for all the speakers. There are these like longer videos of all these talks online.